Wouter. Ik zat weg. Ik? Of, ja, ik heb de stream, althans ik heb het YouTube kanaal voor mijn neus. Maar hij zegt dat hij op dit moment nog niks heeft. Ja, maar ja goed, dat kan natuurlijk even 2 seconden duren voordat hij zichtbaar is.
Hey, en Laurens, voor die vragen, ik heb wel een aantal vragen van Edward en Martijn gekregen.
Ja.
Dus dat is dan in aanvulling op wat er nog gaat komen. Maar ik denk dat ik weet nooit in het begin dat mensen misschien een beetje terughoudend zijn om een vraag te stellen. Dus dan hebben we in ieder geval wat vragen achter de hand. Ik heb zelf ook nog wat vragen verzonnen, maar dus die zijn dan nog extra, zeg maar. Of extra. Die gaan ze niet stellen via de YouTube kanaal.
Ja. Ja.
En hoe krijg ik de vragen van jou op mijn bord?
Ik stuur ze gewoon een berichtje aan jou persoonlijk of via Discord.
Oké.
Dus ik zal het hier even.
Kan ik weer uit mijn share screen modus, Mels? Of ziet iedereen al niet eens met mijn scherm? Nee.
Ja, dat is niet zo handig.
Dat is niet goed.
Mels, ik zit op het Geomaticsday Delft kanaal, maar ik zie hem nog niet. Hij staat ook wat we vanmorgen getest hadden, die heb je weer teruggezet. Oké, want ik zit ook op mijn eigen kanaal. Dus ik zit niet op Geomaticsday ingelogd, ik ben gewoon op mijn eigen Google. Misschien moet je hem even opnieuw linken of zo.
Het is toch wel een beetje exciting dit, jongens.
Ja, het blijft wel best spannend hoor.
Ja.
Ik zal hem even herladen. Ja, ik zie hem. Hij heeft Geomaticsday gewoon de starting erop staan, dus dat is goed. Bastiaan, ik heb jou trouwens een berichtje gestuurd.
Ja, maar ik kan mijn scherm nu niet wisselen. Hè?
Ah ja, dat is waar. Ja. Nee, maar niet. Je hoeft je ook pas te zien op het moment.
Ik blijf nergens aan. Ik kom nergens aan nu.
Nee, snap ik. Inderdaad. Ik heb het geluid nog uitstaan, maar. Ja, ik hoor wel wat.
Welcome to all of you joining us today in Geomaticsday 2020. Geomaticsday is the networking event for the geomatics community in the Netherlands and well beyond. My name is Bastiaan van Loenen. I'm the program director of the master program Geomatics for the built environment of the Faculty of Architecture and the Built Environment, Delft University of Technology. And today I'm going to guide you through the program. Today is a very special day and also very exciting for us, for the students, because they are going to present the results of their hard work over the past 10 weeks. But for the rest of us, it's also special since it's the very first time that we're having this Geomatics Day online. In a normal setting, I would have welcomed you at the Faculty of Architecture and the Built Environment in Delft. But today we're meeting online on YouTube. It's a new adventure for us. The test worked out very well, fine yesterday, but hopefully we do not run into any unexpected issues this afternoon. If we do run into these, we try to solve them as soon as possible, and please accept our apologies already. Okay, well, the program is as follows. You probably have some difficulties in reading the program, so you can also download it on the YouTube channel. If you go to the discussion section and then click on the link right there, then you can download the program. The program has two main components. The first one is, of course, the student projects. And we also have presentations on the business innovation of 4 geomatics companies. The students are presenting their work accomplished for the synthesis project. In this project, they work in a group of 5 on a real-world challenge commenced by an external client. To successfully perform their tasks, the students will have to use all the knowledge and skills that they have developed in the very first year of the geomatics program. And this afternoon, we will see how successful they were. Very briefly, I'm going to introduce the project and also the program. At 1:10, we will start with the project commenced by the Waterschapshuis. And it's about improving the AHN 3 Credit DTM DSM. So if you're interested in that, you stay tuned. And 1:55, we have the project commenced by Esri. It's on machine learning and point clouds for indoor feature classification. The third project is on 3D noise simulation based on advanced input data using automatically generated tints. That's being commenced by RIVM and Rijkswaterstaat. The fourth project is on point cloud deployment for firefighting strategy for the safety region of Rotterdam, Rijnmond and CGI. And that's at 3:45. And the final student project is at 4:30. Commenced by the company 52 Impact, and it is on the strategic approach for site selection of waste facilities in Mexico. In addition to the student projects, we also have presentation of 4 companies. At 1:40, we have the presentation of CDI. Then it's followed by the presentation at 2:25 by Sweco. Then we have the Tensing presentation at 3:30. And then at 4:15, the floor will be for Fugro. Finally, at 5 p.m., we will announce the winner of the Geomatics Best Thesis Award 2019. We will hand over, the chair of the jury, Professor Lars Boden from Aalborg University, Denmark, will hand over the certificate to the winner. As you can see, the winner is not known at this moment, but I'm sure the jury has someone in mind. And after that, we will meet and have online drinks in the Discord chat room. A final word on the format of today. All presenters prepared a video of their projects. And we will first show the video on YouTube and then live stream the Q&A, the questions and answers. Live stream means you can ask your questions in the discussion tab on YouTube. And you can do this already during the video. As a matter of fact, we recommend you to do that as soon as possible. You don't have to wait until the video has ended. You can only post a question if you registered with your Google account. So here you can add the discussion section, and there you can ask your question. So you have to log on to YouTube to ask a question, but we can imagine that you are reluctant to share all your personal information. You also created an anonymous account. You can use this data or this account to log on and then also be able to ask your questions. The questions will be collected and then asked to the presenters, and their answer will be live streamed on this YouTube channel. Unfortunately, it's not possible to have an in-depth discussion with the audience or with the students, but all presenters will be available for further discussions later on in the online drinks, which are at 5:15. And we will share a link to this discussion discussion section of YouTube, and where you are allowed to join us in this online drinks in Discord. A very final note, we will strictly stick to the times of the program. So even if a session ends earlier, we are still starting the next video on the exact time that's been announced in the program. Well, those were my very few words on introducing the entire Geomaticsday. I hope it's all clear to you, and I hope that you will enjoy this very new online Geomatics Day 2020. Now I should say we can start the next video, but we are 3 minutes ahead of time, so we have to wait another 3 minutes before the video of the first group will start. And that video is the video by the first group on the Waterschapshuis group, improving the AHN3 gridded DTM DSM. So we will be back in 2 more minutes.
Hello everyone and welcome to the presentation of the synthesis project Improving the AHN Gridded DTM DSM. Our team consists of 5 people: Martin, Lisa, Khaled, Manos and Christophe. The main supervisor of this project is Hugo Ledoux and Ravi Peters was helping. This project is in collaboration with the waterboards of the Netherlands and our main contact is Jeroen Luzing, the technical manager of the AHN project. A brief introduction to the topic. Currently, the PDOK webpage freely offers a raw point cloud and DTM and DSM raster images for the whole Netherlands in tiles as open data. The majority of people prefer to download the raster images instead of the raw point cloud because it is too big and complex to deal with. However, the DTM and DSM raster images have many flaws that must be fixed. The images are full of no data values. Gaps are visible where cars, houses and water bodies are located. More importantly, some isolated pixels can be found that have no data values, which are caused by the interpolation method that was used to generate the DTM and DSM. Our job was to fix these problems and improve the quality of the AHN gridded DTM DSM. This was a difficult task to accomplish, since the Netherlands is a country that is known for its unique watery landscapes, large rivers and cities with canals. The AHN tiles cover the whole Netherlands, and so a code and a methodology that are consistent when processing all the tiles were needed to be designed. More suited interpolation methods are needed to be developed and tested, and if possible, a hydroflattening algorithm should be implemented to handle water bodies. The project was divided into 3 tasks: ground filtering and interpolation, hole filling and hydroflattening, and scaling, which we will explain right now in more detail. For ground filtering, the national Dutch AHN3 LiDAR dataset is disseminated in the LAZ format and uses the LAS classification codes. Ground points are used for the generation of the DTM, while for DSM all points are used except water points. Initially we decided not to trust the AHN classification, and so we conducted a series of tests with other ground filtering algorithms. Specifically, we experimented with the LAS tools, the cloud compare software, and filters from the PDAL library. Using manually classified point clouds, we measured the accuracy of the results of the different ground filtering algorithms we tested. The analysis showed that the AHN classification can be trusted and that it was our best choice. This is mainly because we couldn't overcome some artifacts in the results of the other ground filtering algorithms without removing whole classes of points from the process. Thus, our final decision was to use the AHN classification, but first we filter out outliers and low noise points before moving forward with the interpolation. Overall, we implemented and tested 6 different interpolation methods, namely Laplace, TIN, Natural Neighbor, IDW, Quad-based IDW, and TIN with constrained Delaunay triangulation that uses polygons as constraints obtained via WFS requests from the 3D-BAH service provided on the servers of TU Delft's 3D Geoinformation Research Group. All interpolation methods were written in Python with the help of packages and software libraries with Python bindings. We visually and statistically compared the results of all these interpolation methods, both for DTM and DSM, in order to identify which ones provide the best results. We calculated the vertical differences between the raw AHN point cloud and the resulting raster images, and we computed the root mean square error and mean absolute error for each interpolation method. Our initial DTM and DSM results suffered from some artifacts that we fixed later with some post-processing flattening algorithms we developed. Laplace interpolation does not leave holes, except in the areas outside the convex hull of the underlying triangulation. However, we plan to introduce them manually, in a constrained triangulation, by adding the boundaries of holes such as lakes and canals as constraints. Unfortunately, this failed because too many LiDAR points fell within the holes, causing them to become triangulated and not represent real holes. It would have been too expensive to remove this computationally. Our final solution consists instead of first interpolating in the triangulation at the polygon vertices and taking the median of the interpolation values per polygon. Hence, its polygon is associated with a height that is based on its boundaries. This method was chosen as we wish to base the elevation of the holes primarily water bodies, on the elevation of their shores. The resulting extruded holes are then burned into the raster. Some polygons were treated with distinction. The client's requirement was to construct surfaces for large rivers which have a consistent slope orientation from source to outlet. We constructed an algorithm that can, for well-behaved river geometries, guarantee such surfaces in the output raster. The first few steps are semi-automatic. First, the operator selects the desired river polygons from the BPG dataset by their names manually. Then a Python script processes them to obtain their skeletons, and then another one prunes them. As branches cannot be removed altogether via pruning, shortest path analysis is then carried out in QGIS to obtain skeletons with all branches removed. From then on, the process is fully automatic. The skeletons and river polygons are overlain in Python, and lines perpendicular to the skeleton are cast on it at its vertices. As shown in this figure, each such line is intersected with the river polygons, and the closest intersection in both directions from the skeleton is used to construct line segments on the line that are effectively river cross-sections. Each cross-section is associated with an elevation by interpolating at their three vertices in the theme inherited from the primary Laplace triangulation. In the next step, the river polygons are rasterized to form a mask that allows river pixels to be identified. All the river pixels are reinterpolated in the raster resulting from the first round of flattening. The interpolation process is as follows. For each river pixel, the two cross-sections in the river between which it falls search for. The procedure involves first drawing the shortest path from the river pixel to each cross-section, excluding them from consideration if this path crosses another cross-section as shown in the figure. Then, the two nearest cross-sections from the remaining candidates is picked, and the elevation of the point is established by inverse distance weighting, using the elevation of these two cross-sections and their distances from the given river pixel. The last stage is a moving window pixel patching step. The algorithm scans the raster, and for each pixel that it still has a no data value, it assigns a value based on its 8 neighbors if it has at least a minimum number of valid neighbor values. This is necessary because where basic flattening and river hydroflattening inserted values outside the convex hull of the theme constructed in the primary interpolation, tiny holes may have nucleated. This simple algorithm can patch this in with sufficient accuracy. Scaling focuses on two aspects of data processing: the sheer size of the data and how to reduce artifacts along borders when connecting different tiles. One of the first steps done was determining the tile connectivity between the different AHN3 tiles, as this allowed us to retrieve information for a tile from its neighbors later on. The size of the data was tackled by reducing the size of each tile that would need to be processed. This was done by splitting each AHN3 tile into 20 smaller tiles. This also allowed us to create a buffer around each tile, which is necessary to avoid artifacts around the borders of the tiles. All tasks were executed in a scalable framework, which allows for easy addition and adjustment of algorithms during the development process. The framework relies on different task workers which retrieve a new task from a queue. When they finish processing a task, they report the result and continue with the next task available in the queue. Depending on the workload of the algorithms, these workers process as many tasks as the number of available threads. In our case, this was limited to 5 workers working concurrently due to the memory bottlenecks we encountered. Most of the artifacts were avoided thanks to the buffers around each tile, but some new ones were introduced by water flattening. This is because for each subtile, the median value calculated for the water is slightly different, resulting in visible patchwork where water is present. This has been countered by running an extra post-processing step, which takes the final raster and applies the same water flattening step to it, taking the mean of the different patches of the water as its value. This ensures that for a single tile, all the available water polygons are equalized. After running for around 5 days, the program was able to process around 40 AHN3 tiles, creating both DTM and DSM outputs. It processed over 500 GB of data and used up to 100 GB of memory. To be able to process the whole Netherlands, the program would need to be efficient enough to process 1,100 tiles. Overall, the results of this project have been satisfying. As you can see, the DTM and DSM both have been improved compared to the original dataset. The accuracy of the already present data has not been reduced, while all the missing data have been given a representative value. The addition of water flattening has shown to be a great and necessary addition to the pipeline. Having this method as part of the processing pipeline adds a lot of value, especially for a water-rich country such as the Netherlands. Currently, the available water polygons are used to do so. However, we believe it should be possible to do so entirely with algorithms, which was proven in a small proof of concept we have discussed in more detail in our report. One of the remaining challenges is to be able to process all of the AHN3 tiles within the Netherlands. We set out to be able to process all 155 tiles within South Holland, and we have been able to process around 30 tiles as DSM and about 50 tiles as DTM. The memory bottlenecks encountered were more severe than initially expected, thus resulting in being able to run less threads and having fewer completed DTM-DSM tiles. Nevertheless, the main goal of this project has been to improve the AHN grid DTM-DSM, which has been a success. All of our code is available as open source code and it can be found as a GitHub repository. Thank you for listening and we hope you enjoyed. If you have any questions, let us know during the Q&A session.
To make this remark, we do not train the students in making very nice videos. Yeah. So I have to speak again, what? Ah, very good. Okay, well, we are back. We are now in the chat room where we're going to answer the questions of the audience. I must say it's very impressive video, and also the research that's presented was quite impressive. And I must guarantee the audience that we're not training the students here in making these nice videos. So impressive. Anyway, some questions we have already. We have a question by Jeroen Leusing, who's the supervisor from the Waterschapshuis. He asked, how long would it take you to generate the whole Netherlands?
Yeah, so I can answer that. I'll grab a quick graphic, which wasn't in the video, but is available in our report, and I will share that. So if Mels can pick that up, that would be great. So this is an overview of the different steps that are taken to generate the final result. And as you can see, currently all the steps are reasonably optimized, except for the DSM step, which is mainly a limitation of using Python and using a lot of data. So for the whole of the Netherlands, the estimate right now is kind of disappointing, would be around a month of processing, I guess. All right. That's okay. I'll just wait for the figure to appear. Yeah, there we go. Okay, cool. Yeah, so as I was saying, the DSM is the step that takes the most time, mostly because of Python, because it's just calculating a value for each raster cell. So it needs to go over a bit over 6 million raster cells. So that takes a lot of time. So right now, the whole of the Netherlands would be around a month. But if the DSM processing were to be reduced, then this could be brought down to probably somewhere around a week, I guess. But it's hard to say.
So a week for the entire Netherlands. Very good. A question by your supervisor, Hugo Ledoux. How do you deal with a potential shift between the AHN3 and the Bach BGT polygons?
Yeah, so just to recap on what we use these polygons for, we use Bach, which are building footprints, to work. Has it loaded?
Yeah, works.
All right. Just to clarify, we didn't use the Bach building footprints in the final configurations because for that we would have needed a better match with the point cloud, and because our algorithm was meant to be used primarily with water bodies. So the way it works is it picks I guess it interpolates the vertices of the polygons inside of the primary interpolations TIN framework, and then it takes the median of those values. So even if there are a couple of mismatches in terms of where the vertices that are interpolated, so they can, for instance, if it's a lake or if it's a canal, it might slightly overlap with a street, and that could be problematic. But because the majority of the boundaries or vertices would still be in the right area, and because we take the median in the end, the result would still be satisfying. And one thing that we could do to eliminate this issue, I think, so this is not explicitly dealt with in the code because it hasn't caused any major issues. But one idea I had, just reading this question, would be to use the default classifications of the AHN to select specific points. This would of course just this would only be available for DSM, because for DTM generation we pre-filter the data for ground points, so there we couldn't rely on classifications. I think that answers the question, but whoever asked the question, please, yeah, Hugo, if you have more detailed questions about this, then please do go ahead and state it in the YouTube channel.
Thank you very much for this answer. Moving on to the next question, because there are lots of questions. Very good. A question by Robert Fouten. His question is, did the water surfaces themselves give you difficulties?
Yeah, so maybe Lisa can elaborate a bit on how she created those water polygons.
Yeah, so it did in the first part give us more difficulties because there are not much LiDAR points in the water. So that's why we decided to go with with finding polygons. So we did go over a few data sets, such as the BGG, and some others. But what we wanted is for the hyperflattening to have the rivers separately. So therefore we were searching for a polygon set where the different polygons were classified differently. And so the BGG was the solution to that. And from there on, it wasn't that much of a difficulty, because then we could use the not river polygons to do the normal interpolation on, and that helped a lot.
To elaborate on that a little bit, the Beker here is another data set on PDoc, which has good quality polygons for water. It has further classifications for types of water bodies and even sub-classifications for names of rivers. So we could use that to distinguish between, for instance, rivers and lakes and canals, which was useful for deciding how to treat which water body. I guess we had 3 classifications. We had big water bodies such as lakes and the shores of the North Sea, and we had canals and the rest of the stationary water bodies and then rivers, which we hydroflattened.
Very good. Thank you very much for your answer. We move to the next question, and the question is by Rafi Peters, also one of your supervisors. He's asking you, you mentioned in your report that the different AHN tiles are classified by different parties. Did you investigate the different qualities that resulted? So will your method work equally well for all AHN tiles?
Shall I answer that, Manus? Yeah. Okay. Hear me well?
Yep.
Oh. To cover all the point cloud like that is collected by different parties, we tried to investigate on tiles from different areas in the Netherlands. So, for instance, we got one from Biesbos, like the Biesbos city, and one from in Amsterdam, one in Delft, and one in Groningen. And the quality showed overall like similar, like equal quality. Like the investigation showed equal quality for all the point cloud classification at these areas, but specifically like which party collected which point cloud, we haven't investigated that specifically. I don't know if that answers your questions, but in general, the algorithm should work with similar, should result in similar quality output for the whole country.
So, okay, you addressed that in your report. Another question by Rafi is, you mentioned building flattening in the report, in addition to hydro flattening. Why would you do building flattening?
Can I answer that?
Yeah. Okay. Yeah.
All right. So this was not our own idea. The reason why we proposed to flatten buildings was because our client himself stated that this would be good. They are, the client company, familiar with tin-based interpolation methods, even though AHN used IDW, which is very different from the tin-based methods. But even though the tin-based methods are continuous across holes such as building footprints in DTMs, they result in, especially the simplest ones, such as linear interpolation inside of tins, can result in triangles appearing even in the interpolated rasters. So that was a particular interest to the client to try to eliminate those. And his original suggestion was to, instead of interpolate inside of the holes, we try to figure out how to just give them a constant elevation, which would constitute flattening the building footprints. And we tried this, but there were 2 concerns. So if we treat them the same way as we treat the water bodies, their elevations are not just rough estimates, they are wrong estimates, because building elevations should not be decided based on the elevations, interpolated elevations of their boundary vertices. it should rather be based on all the LiDAR points which are found inside of the interior of those footprints. And that is really computationally expensive. So we didn't, in the end, try this. Well, we did try it, and it proved to be too expensive. And we used methods such as natural neighbor interpolation and Laplace interpolation, which do not yield such disruptive triangles inside of the end results. So we did not think that it was a serious enough aesthetic concern to justify the extra computational expense.
Super. Thank you very much. I think it's about time for the final question. There's a question by Peter van Oostrom, professor at our university. Could you sketch your algorithm to detect the water bodies from the LiDAR and not needing external data sets?
So I can try to answer this question. We didn't really go into it, so it would be a really basic algorithm. So, but while in water bodies there are not that much LiDAR points, and some points are even classified as water bodies or water points. So what you could do is, like, if you have big holes, like if there is in a radius of certain points no data or no other points, you can get the boundary, like with an alpha shape or something like that get the boundary of a hole. And if there is like one or maybe more water points in there, you could say that those are water points. And that would work for all the big water bodies, but really small water bodies where there are no water points in, it would be kind of difficult to decide if those are water bodies or something else, like maybe something that was moved, or yeah, I don't know. So for the big water bodies, it wouldn't be that hard, but for the smaller, it would be really difficult to extinguish them from different things.
Thank you very much. Normally you would get a big applause from the audience, but the audience is, well, it's there, but they're not applauding for you. So I guess I do that for you. Thank you very much. Thank you, thank you, thank you. It's really good. So we say goodbye to you now, and we get prepared for the presentation of CGI, which is entitled From Indoors to Outer Space, Graduating and Working at CDI. Will be 2 minutes before we will be back to you.
I'm Robert Fouten. I'm one of the old geodesy students. Geodesy is one of the predecessors of geomatics, of course. And after my military service, I joined CGI, where I'm now working as a vice president consulting. And CGI is a large Canadian company, roughly 80,000 people working worldwide with us. And we have 600 specialists working with us doing GeoIST work, of whom 80 are located here in the Netherlands. And they work together quite significantly in a very active practice. As said, we work together with the academic field. We have our own research group in the building in Rotterdam, when we can go back to the building, of course, which probably will not be happening before September. And then what is our focus? I think there is a focus on the research that we're doing more or less on operational geo. You will see in one of the presentations today that we do a lot about situation awareness. 3D digital twins is very important for us, but then we have a focus within that world on indoor 3D digital twins, which we use for modeling how to get the data of these buildings in a very fast way into a model. And of course, remote sensing is also part of our specialty, and about that you will see another presentation today.
Hi, I'm Peter. You're an intern at CGI. Can you tell us something about yourself?
Hey, Lawrence. Yes, of course. So I'm an intern at CGI, but I'm also a master's student of study Geographic Information Management and Application, GEMA in short. Right, I've just finished writing my thesis for the University of Delft, and I'm now starting an internship.
And what do you think about the working environment at CGI?
Yeah, I think it's very good because, of course, now we have Corona, so everyone, or we don't have Corona, but the Corona situation. So everyone is working from home, and that's working pretty all right. But I liked it way better when we could still just work at the office, because there are more interns there. So there are other students who are also working primarily at their thesis. From different backgrounds, but all related to GeoIST. But there are, of course, also other employees who you can ask and consult about your topic. So I think that's really, really nice. Okay, nice. You did your thesis at CGI. Can you tell us something about it? Yeah, of course. It has 3 different aspects. The goal is to facilitate first responders with situation awareness. And situation awareness is like a sense of what is going on in an operation environment. They do have quite a good sense of what's going on for outdoor scenarios. So for example, where are fire trucks driving, or how can they navigate best to a certain incident? But they don't have the situation awareness for indoor environments. So the question they asked me is, could you research how we can improve the situation awareness for indoor operations? Because there's very little information available. So, for example, there are very few floor plans available to fire departments. Then especially 3D data was almost unavailable overall. So we will map an environment, so make a 3D model of it, and simultaneously track a first responder while he is navigating that environment.
Carl.
Hi.
Can you tell us a little bit about yourself?
Yeah, of course. My name is Carl van Winden. I graduated from Geomatics in 2014, and I've been working for CGI ever since. So I'm working for CGI for almost 6 years now.
Mm-hmm. Yeah, that sounds good. And what kind of projects are you working on?
I'm doing multiple projects for ProRail, which is the National Railway Authority in the Netherlands. And they are responsible for the rail infrastructure and schedule in the Netherlands. And one of the projects that I'm working on is the schema application. This is an application where we developed an algorithm that automatically generates the schematic representation of the railway based on a geographic representation.
That sounds very cool. Can you maybe show us a little bit of this application, if that's possible for you?
Yeah, of course. Onto the map. And we can, for example, zoom into a specific situation. So in this case, that's Putten. By drawing a polygon, we can select the railway tracks that are underneath it, and we see which railway tracks are selected. Then we can draw a reference line that we need to create our schema. And if we generate the schema, it will automatically make a schematic representation of the railway tracks. This is really useful because normally this is done by hand by a lot of people at ProRail, and now we want to automate this. And it also has the advantage that it's faster, but also that it's possible to generate a schema or a schematic representation of a bigger area of the railway.
Can we go back to you and working for CGI? Could you maybe tell me a little bit about working for CGI? How is it, and how do you find CGI actually in the context of working as a geo person?
Yeah, I really like working at CGI, also because we have a big geo-ICT community where a lot of people are working and really focusing on the geo-ICT part of our work. Mm-hmm. And I really like that we're a really transparent company where you can work on big projects and also have, nice and fun challenges inside your work. And you really see that we have an impact on day-to-day business for our clients. And besides our challenging projects, CGI also offers a lot of possibilities to grow your career.
Yeah, that's correct. Yeah. Okay, thank you so much.
Hello, Auke. Can you introduce yourself?
Hi everyone, I'm Auke and I'm working at CGI now for almost 2 years. I got to know CGI during my master thesis. I wrote my master thesis at CGI in combination with the Ministry of Defense, and I really liked it. I think CGI liked me too, because afterwards they offered me a job.
What projects did you do so far?
I'm now currently working on the Mission Landing Zones project for almost 5 months.
Okay, cool. It's nice that you can work a little bit more on your thesis. Can you give us a demo of the Mission Landing Zones project?
Yes, of course. I will share my screen. In the Mission Landing Zones project, we're calculating where the Ministry of Defense can safely land helicopters. We're doing this by calculating the requirements the Ministry of Defense set. You can think of requirements like the size, the slope of the terrain, and the surface of the terrain. In this case, we're looking at the water. Water is set as a requirement where helicopters cannot land. In this case, we took Sentinel data and we can calculate the water in the area and make it a sublayer. Another example which we use is clouds. Because we don't know what is beneath the clouds, we need to find the clouds and mask them so we can make sure we know exactly where helicopters can land.
Okay, thanks. I think we know enough.
Welcome back, everybody. You've seen the 3 videos about indoor, about schematics, and about remote sensing. And I hope that you like them. And finally, I would like to close this CGI session within the Geo Day to tell a little bit about the internships that you can do at CGI. Of course, we also always look for employees, but I think internships might be at least very interesting to share with you. The internships can be both a normal and short internship or master thesis projects. And what we see is that we do a lot of work together with Geomatics. Both the Indoor Lab and the 3D Geo group at Geomatics are engaged with us. And what we see is that many of the students that do their master thesis with us also write a scientific paper together with us and the university. It's not something that you have to do, but you can do it, and it's sometimes it's very nice. Of course, we contribute to the Geo Day every day, and we give lectures as part of the courses at Geomatics. We've done the GeoWeb thing, and at this moment we also contribute in the synthesis project. And there will be a list of topics that we can share with you, topics for internships that we think about right now. But it would be a little bit too much for this presentation, but there is a complete list, but also we're open for your own ideas about that, of course. With that, I would like to close the CGI talk in this video. Thank you again for participating, and I hope to see you later on. And I know that there will be a special channel for people that want to join us in an open talk afterwards. So please join CGI in this specific meeting afterwards. Thank you. Goodbye.
Okay, welcome back to the Q&A. As far as I could see, I don't see any questions from the audience, so then I guess I have to ask some questions. You listed, you addressed that there is always space for internships and master theses that they can do in your company. Do you have any specific hot topics that you would really like to have a geomatics student to do for you?
Yeah, sure. Thank you, Bastiaan. At this moment, the most of our internships deal with two themes. The first and maybe most important theme for today is all kinds of indoor geomatics, indoor 3D, modeling, positioning, and the link, as you've seen in the movie, with situation awareness. I also strongly suggest you to see the part of the team that is working together with the Veiligheidsregio later today. That's showing quite well on what track we are. The second theme is high precision photogrammetry outdoor. So how can we deal with gathering objects in the outdoor world and position them as well in the highest accuracy that's possible. And so far we used a lot of drone imagery, both LiDAR and photogrammetry imagery to do that. And that's another type of research we're working on. Then there are some very specific themes, but I would also say, if somebody's interested in a company like CGI, just come forward and tell us what you want to do. We have a limited number of internship places available at every time. So maybe we say yes, maybe we say no. It's not completely open.
Thank you very much. I do see a question of Peter van Ooster, but I'm not sure if it's related to your presentation. For the real schematics, could these be treated without drawing a reference line?
Oh yeah, that's a good question. It relates to our story, yes. Good question, thank you, Peter. Yes, it can be drawn. What we're doing now is getting the reference line out of the pre-existing data. So far we just draw it manually, which is in the process of developing this software, a handy thing to do. But we will automatically generate this reference line later on in the process.
Okay, very good. Well, it's always also almost time to go to the next presentation. Again, if you want to join CGI for further discussion, come to their Discord channel. I think it will be shared, the link. We share it in the chat box. And then we move on to the next presentation, which is again students. Students presenting their work that was commenced by Esri on machine learning and point clouds for indoor feature classification. Thank you very much, CGI, and we'll continue with the rest of the program.
Hello everyone, I'm really glad you could join us this afternoon. My teammates and I are extremely excited to share with the world what we've been working on for the past 2.5 months for our synthesis project. Our project is called SciPOC, Semantic Classification of Indoor Point Cloud, and it uses deep learning at its core. We did it in collaboration with both Esri and the Dutch National Railway Company, the NS. Now, before I begin talking about the project itself, let me introduce you to our team. During this presentation, you'll get to hear each and every one of us. Firstly, we have our project manager, Mels, who has coordinated the entire project. Our technical leader, Jai, who has always made sure that the technical aspects of our project were on point. Our quality analyst, Dida, who has strived to double-check everything and who ensured the continuous quality of our deliverables. Our product manager, Shawai, who has made certain that we were doing what was required by our mentors. And last but not least, myself. I handled the communication with the outside parties all throughout the project. Of course, regardless of our predefined roles, we all work together side by side to make this project a success. Now, this is our research question, which encompasses the main essence of our project. It may seem like a very academic formulation, but what we were basically asking ourselves was, in very non-technical terms, can we teach a computer to recognize various elements from an indoor environment, such as furniture or vending machines, or plenty others? Of course, you'll find the answer to this question in a bit, but for now, we need to mention the most important element of our project, and that is deep learning. Deep learning has been our main tool, which we have used all throughout the project. What is deep learning exactly though? It is a mechanism which is used for training deep neural networks. These are neural networks which contain a number of hidden layers. A deep learning algorithm does it all by itself, unlike a machine learning one, in which a developer may intervene. Our features are also automatically learned by the network, which in turn makes it a bit more robust than a machine learning algorithm. Now, of course, there are lots of things which can be mentioned about deep learning, but for the time being, we would like to tell you more about the project itself rather than the theory behind it. Should you be curious to find out more, we invite you to take a look at our paper, which will be online on the TU Delft's website pretty soon. There, we also provide more background information as well as external resources which we will introduce the reader to the world of deep learning. For now, though, I will give the spotlight to my teammate Jayu, who will tell you more about the first part of our project.
Thanks, Alex. As we know, a point cloud is a set of points where each point is a vector of its 3D coordinates, and maybe with additional features. These points often contain rich information, but they are unordered and is topically distributed in space, which makes it really difficult to handle for a typical convolutional neural network. In this project, we explored the possibility of several neural networks as listed, named PointNet and PointNet++, PointCAN, DGCAN, SuperPoint Graph, and BotNet for indoor point cloud classification. These networks vary in their designs, but here we will not dive into the details of them. We will, however, take a closer look at how PointCAN works, because this network was eventually selected by us for the case study. As we said, the point clouds are unordered, so if you look at the convolution inputs for regular grids and for the point cloud as shown in the figure, by following orders as illustrated, the convolution operator for the second, third, and fourth scenarios could be computed as shown in the first equation sets, respectively, which means that a direct convolution will lose the shape information while caring about the orders, which is undesirable. For PointCAN, a k times k dimensional X transformation for the coordinates of k input points is learned with a multi-layer perceptron. This is called the XConf, and it is the building block for point CN. The XConf for these scenarios can be formulated as the second equation set, respectively. As you can see, with an ideal X transformation, the XConf is capable of being invariant to the ordering. In regular grids, convolutions are recursively applied on local grid patches. Similarly, with point clouds, XConf is recursively applied to aggregate information from neighborhoods into fewer representative points, but each of these representative points has richer information. We used the Stanford large-scale 3D indoor spaces dataset to evaluate the performances of these networks. The dataset is split into 6 areas. We trained the neural networks on area 1 to 5, and we used area 6 for evaluation. The evaluation result shows the point CN and the superpoint graph are most competent. While considering the superpoint graph needs a lot more pre-processing and complex configuration, we therefore select the point CN for the case study implementation. Next, Miles will take over and introduce the case study on the NS dataset.
All right, thank you, Zayu. During the project, we got the opportunity to work with the data provided by the NS in order to test our research in a real-world environment. They wanted to look into the opportunities that deep learning would provide them when using this on the scans they performed in their stations. For our case study, we focused on Amersfoort Central Station, which can be seen on the screen. We did this with the aim of labeling the points in the currently unlabeled RGB-enhanced LiDAR data with a class code showing the identity of the point. This would allow for this data to be used in all kinds of applications, such as in asset management on stations. The benefit of a network is that it is a fast and automatic process and reduces a lot of the manual labor, potentially saving hundreds of man-hours. As the data was unlabeled, so unfit for training, we needed to do all of the labeling for our experiments ourselves. This meant looking at the scene and labeling objects such as entrance gates and information signs. In total, we distinguished 18 different classes, which we all labeled using ArcGIS Pro. We first converted the 19 different scans we acquired into the LOS format and then merged them together into one before splitting them into smaller regions with a 5x5 area, as can be seen on the right, for more efficient processing. Now we'll show a short demo of how this labeling process went in practice. When in ArcGIS, you first add your data into the map like this. Then, as we are pretty far away, we zoom to the layer and change the visualization to RGB to get a better view of the scene. Then, we can rotate the scene and look for the object we want to label. In this example, we take this yellow egg. We then rotate the scene once more to make it easier to create a profile viewing, which zooms in on the data for easier selection of the unwanted points. In the profile viewing, we then get a good angle to see the object of interest and select it using the Select tool. The selected points, shown in blue, can then be labeled as the class we want, which is 1 in our class code structure. To see the change, we can then take a look at the statistics of the loss file, where we can see the class code of 1 now as entries, or we go to the symbology again and set the visualization to classification, where we can modify the color for the class we see, and we can see which points are labeled as which class. As we have talked about preparing the data, Gita will now explain the experiments we have done during this project.
Thanks, Miles. Okay, now we have labeled point clouds with 6 different objects, which are yellow eggs, garbage cans, couches, entrance gates, ticket machines, and vending machines. We separate them into training, validation, and testing, and we train for about 6 hours. Here is the initial result. We can see from the graph that our training cannot converge. And from the evaluation, we can see that almost all points are classified incorrectly. So why is that? Here we can see clearly that we have unbalance between labeled and unlabeled points. More than 90% of our points are still unlabeled, and that may cause the training cannot converge. Besides, the geometry of many objects are not fully scanned. So based on these initial results and feedback from our mentors and clients, we try another approach. Here we cut our bounding box, so we have a smaller scenes now, and we relabel them by adding new classes, which is floor and other classes. And we clean the dataset by removing people, floating points, or other clutters. In this experiment, we didn't separate the training, validation, and testing because we only want to see whether we can get some results. And here is the results. Now we have a high similarity between prediction and ground truth. From this experiment, we get the overall accuracy around 0.9 and mean IOU around 0.8. And from this training, we apply the training model into a different data set outside our training data. Here we can see that some parts of couch here are classified as garbage can. Meanwhile, the floor and garbage can itself are correctly classified. Notice that we have unlabeled floor in the ground truth here. Next, we go back to our large scene. Now we apply the approach from the small scene. We add new classes, so we end up having 18 different classes, and we separate them into training and testing. We have one for training and one for testing. So here we can see that the ceiling and the floor have a fairly good result, but here when we zoom, the second floor are classified as ceiling. Here is the same result, the ceiling classified as the floor. And for the entrance gate here, we can see that the entrance gate are variously classified into different classes. So from this result, we may need more training data to get better results. Last, we try another approach based on Kudinov. We only focus on the one object, which is a yellow egg. So we collect all yellow eggs we have in the station. We have 9 yellow eggs, so we separate them into training, validation, and testing. Interestingly, by using the same parameter with the previous training, we only get the overall accuracy of 0.29. But when we reduce the block size, the overall accuracy increased significantly into 0.8. However, how the block size affect the overall accuracy still need to be studied in the future. Okay, so now we move to Xiaoai. Xiaoai will present about the web application.
Thank you, Lida. In this project, we also developed a web application for users to get semantic segmentation results in a more friendly way. The picture shows the technical architecture of this app. For the front end, we use Vue as our main JavaScript framework. We also use Bootstrap to make our web pages more responsive. 3JS is used for the 3D visualization. For the backend, we use Flask, which is a lightweight web application framework. We also use Circular3 as our database. To transmit data between the clients and the server, we use Axios to connect the front end and the back end. For the functionality of this web application, it provides 3 main functions: file uploading, downloading, semantic segmentation, and result visualization. The picture on the left shows the process of file uploading. The app requires the user to provide training datasets and testing datasets. If the user wants the process of validation, they can also provide the validation datasets. The picture on the right shows the process of segmentation. It contains 5 steps. After TensorFlow sampling, compiling, and dataset preparation, we can perform dataset training, testing, and validation. For the result visualization, we can see one good result on the left animation, since you can see the prediction and the ground truths are quite similar. However, the result on the right animation seems a bit messy due to more kinds of entities in the scene. Now Alex will give a conclusion of our project.
In the end, we would like to thank our mentors for being there for us throughout the project. Meeting up with them every Friday has been awesome, and they really helped us along the way. and they have always been available for us whenever we had a misunderstanding. We truly hope that you enjoy our presentation. Should you have any questions, feel free to ask us in the YouTube chat, as we'll be here to answer them for the next 15 minutes. Thank you.
Okay, and we are live over here. Now I can actually stay here. Also nice for a change.
Very good, and again, an impressive video. We do have some questions, and we start with a question by the supervisor of this group, Martijn Meijers. He asked the question, given that the training phase took really a large amount of time, what would be ways to improve this tedious process? Who can I give the floor?
Sayu, I think that you wanted to take this one.
I can take that.
Mm-hmm.
I can take it. Can you hear me clearly?
Yeah.
Yes.
Okay, super. That's indeed a question, Martijn. Currently, I can say, unfortunately, there's no magic for us to deal with that. That's a way that we have to take for the long-time training. In our project, the training was almost done on my local PC, and it has really taken a lot of time, as you can imagine. And as you can also see, the epochs and the training time in our reports. But what we can do, as I said, is limited. But what we could do is for the experiments, we can monitor the process of training, and by logging the process, for example, we can take a look at the TensorBoard. If you are familiar with the TensorBoard, that's a GUI for us to monitor the training process. So we can see from the TensorBoard, is the training overfitting, or perhaps is the network not learning anything meaningful? So if that happens for some cases, and it did happen in our experiments, so in that case we can terminate the meaningless training early, so that we don't waste additional time. And by the way, that's called early stopping. Yeah. Aside from that, I guess our only way is to maybe change to more fancy hardware like that. Yeah.
Yeah, to tack on that, it's also one of the strengths of deep learning is that we take one time a very long approach to learn a network, and then afterwards the classification, which is actually used at the companies, is done in a matter of minutes. So it's also a method that initially takes a lot of setup time, but then in the end, actually deploying it will take significantly less time. So in that way, we don't the final product that we deliver does not take that long.
Very good. We move on to the next question, also by our supervisor, Edward Verbrey. He's asking, your client is Esri Nederland, and so not Esri Incorporated in Redlands, USA. Mm-hmm. How do you sell your research and development to the mother holding Esri Incorporated? Should this kind of deep learning semantic enrichment be part of ArcGIS Pro? Who are going to be the users then?
Mm-hmm.
Who will answer this question?
I think I can answer this question. In this project, we did develop a web application to integrate what our research part into application one. However, I don't think we will make this kind of deep learning stuff to be part of the ArcGIS Pro. At first, we did try to make our research part into add-in in the ArcGIS Pro, but actually the deep learning projects and the neural network setup has a very high requirements for the user computer configuration. So we do prefer a web application to integrate the research part. And I think the users, since our project is for the indoor semantic segmentation, So I think it will be useful for the users to do some 3D modeling, like the indoor objects or the indoor navigation part. So that's all.
Yeah, to tack in on that answer, so for our purposes also, our PCs had some issues with the total loading time that we have on ArcGIS Pro, but the functionality that we have implemented can obviously be taken up and can also be integrated into ArcGIS Pro itself. So it's more that during this project, it was not feasible for us in the same time to integrate it already, but the method that we are using can be added. And right now they already have some automatic segmentation algorithms, such as for ground filtering and for classifying buildings, which they do on a lot of data they already have. So in a similar fashion, our code could also be integrated as a option for the users to use in ArcGIS Pro. But this is something that's a more that we as a group of students to get that integrated into the entirety of ArcGIS Pro, that was not feasible during our project.
Okay, well, you talked a lot about ArcGIS Pro. There's also a question by Hugo Ledoux. I saw that you're using the open source and free software Cloud Compare to view and explain the results. And how did it perform if you compare it with ArcGIS Pro? Can you say something about that?
Yeah, so what we noticed also during the labeling process was that if there is a lot of data that we need to process on our local laptops, because we were pretty hardware limited during our project, then ArcGIS Pro sometimes cost too much time for our laptop to compute with it. That is also due to me not having that good of a GPU, so the visualization would run out. So for that purposes, we sometimes shifted to Cloud Compare, because in overall the total loading time that Cloud Compare needed for for what we did was smaller. So also if we wanted to cut up the data just in like linear lines, then Cloud Compare would perform better. But for all the intensive labeling applications and for the more in-depth options, and then ArcGIS Pro won by a landslide. So it's dependent on which steps we had to take. But to save my laptop during the labeling process, for validation, we often switch to Cloud Compare, because that was easier and it caused less overheating problems with my laptop. But that's also because of the, it was mostly due to hardware limitations.
Yeah. Okay, thank you very much. Then we have a question by Jos. Say that some group of people develop a tool which want to classify point clouds in near real time. Could that be done with your method, or if it's already been trained?
Yeah, so Gita, I think that this is mostly in your case because you did most of the classification in the end.
Yeah, I will try to answer. So if we already have the pre-trained model of
Your
into
yeah. I think that your
then
voice is sometimes dropping.
Oh.
Yeah.
Is it clear now?
Yeah, I can hear it now.
Okay. So for the pre-trained model, we can use the, but we need to notice that another scene having the similar. So for example, we train in the one NS station, we can run the another scene of the station. But if we want to run, for example, to airport, we cannot do that because they simply having different feature.
Yeah, the training that we did on indoor scenes, it's very location dependent, because every indoor building it's different. So if I train on chairs in, for instance, a library where you have a lot of couches that you can just plop down into, and if you compare that to a bar, yeah, that's just totally different furniture, which makes this harder. But if you need focus on the location already and train on the location where you want to run it, it should be feasible.
Okay. Then we have this question by Liang Yang Nan. Did you compare your method with other existing methods? And what would be your conclusion?
Zayu, I think that this is more for your. part of the project?
Maybe I can try to answer that.
Yeah.
Maybe I can try to answer that. Actually, we tried. If you see our presentation, well, we don't have it again, right?
Mm-hmm.
But if you see it again, in the methodology part, we actually compared 5 or 6 existing state-of-the-art neural networks for point cloud classification, and that includes the PointNet, PointNet++, and PointCNN, and DGCN, and that also relates to the question by Chirac. Is that right? Yeah, because
yes,
we also use the graph-based neural networks. So I hope that answers the question.
Yeah.
So we actually compare different types of neural networks.
Yeah, and to tag in on that, on the methodology part, also during the experiments that we had, for which we performed 4, each time we changed some steps in how we want to validate it and how we prepared our data for it. So not only did we test with multiple neural networks, but we also tested with different methodologies, of which some were proposed by one of our mentors as well, Jesus Balado Frias. And some were proposed also as experiments that Esri has performed in the past. So we've also based our experiments on approaches that were already tested.
Very good. Then a question by Dongyang Peng. Was your algorithm of machine learning from a library, or did you implement the algorithm yourself?
I could answer that. No, it was from a library. It would have been much too difficult to implement a deep learning algorithm in just 2.5 months. It's a lot of research, so we were just using other algorithms and seeing if they can work well for our application.
Yeah, it's also for the purpose that we wanted to do with the project. So we wanted to see how the machine learning that is available right now can face in a different environment based on a different location, because a lot of research has been done into imagery and also in the outdoors. So we wanted to focus more on how value can be added to the indoor and the point clouds. So because this was the main focus of our research, we opted not to implement it from scratch ourselves.
And talking about the indoors, Robert Foute asked, did you also take a look at the indoor parts in trains?
Well, so this is more of a question related to the data that we were provided. So from Remco Blunder, sorry, we got the data for Amersfoort Central Station, which we focused on during our project. And in the scan of this station, they opted not to go to the tracks because there was a lot of people traffic there, and in the stations it was less. So for privacy reasons, we do not yet have those parts. So as a consequence of not having it in the data, we have also not done research into how we can see it in the trains. But it is something that we could potentially pick up for a continuation or for future work on this project.
Very good. Well, then it's the final question. It's quite a long question by Edward Verbree, your supervisor again.
Mm-hmm.
You enrich point clouds with the semantics, but points are still points.
Mm-hmm.
What are your ideas about rich, smart point clouds? Will they have more value for the user above derived products like 3D voxels or the 3D LOD models? Brief answer, please.
Okay, so brief answer, it depends. It's
yeah, right.
Yeah, because it's data, it really depends on the application that you use it for. So for instance, for the asset management that we focused on as a potential added value, knowing which points are which object will probably have more value to the user than in which voxel it is. But if you just want to, for instance, if you want to make a 3D model of the whole scene, then having a voxel-based structure can potentially be way faster and way more efficient. So it really depends on the application.
Very good. Brief and concise answer to this final question. And this makes us conclude this session. And again, I will give you the applause, and I hope that the others will join me digitally. So a big applause to you for this very nice presentation and discussion.
Thank you.
You're very welcome. And then we move on to the next part in the program, the presentation by Sweco, 3D in a landscape of 2D registrations.
All right.
And I think Mels can press the button now.
I will do so.
Good afternoon, everyone. I hope you're all doing well in these crazy times, and I'm glad we can still do some form of Geomaticsday in this digital way. Today, I would like to talk to you about 3D in a landscape of 2D registrations. My name is Fanny Strayer, and I work as a software advisor at Sweco. At Sweco, we are focused on designing the cities and communities of the future. And as a GIS department of Sweco, we focus on the digitalization of these cities and communities. And we work on providing data so that analysis can be done on these things. And there's a number of software packages that we develop as a GIS department. And here you see some examples. One is a GeoWeb that we've developed together with Esri, which is a GIS package. And another example is of Observe, which is focused on the maintenance of different types of objects that are outside that are in responsibility of municipalities, such as trees and roads and playgrounds, etc. Move 3 is our geodetic package, which is focused on geodetic computations. And I work for DigiDialog BGT, which is focused on the BGT, or the base registration map of the Netherlands. In our software, this is what the BGT looks like, specifically the surroundings of the Faculty of Architecture, as you all are all familiar with. And as you can see here, the BGT is really focused on digitizing all objects that are larger than 30 centimeters. And together, that forms a complete base map of the landscape of the Netherlands. It's all basically flat, even though all topologically correct. But most of the focus of the BGT has been on forming a complete 2D map. But more and more users are starting to see a lot of good reasons to form this 3D or use more 3D information. A good example are the water boards, who are very interested in 3D, specifically height differences, so they can analyze the water flow through the surroundings. So for them, we're already registering the BGT in 3D. Specifically, what we can do within DigiDialog BGT for this base registration is to provide the collection, the storage, mutation, and usage of this data, and it all goes through a cycle constantly. And within this collection, we have a lot of interesting options to provide for very reliable data. For example, we have very direct connections with different GPS and geodetic collection methods. And we also have direct couplings with photochromatic packages. Also through direct coupling with StreetSmart, we can collect in 3D also from panoramic images and also from point clouds that are behind that. And we are working on couplings with point cloud software. All of these collection methods are focused on getting 3D measurements, but most of our customers are throwing away the height information because the BGT is up until now mostly focused on 2D data. And a lot of our direct users, or the people who are responsible for the mutations in the BGT, don't see a direct use for this 3D information. But more and more of our customers and more of specifically the users of the BGT see a lot of reasons to start collecting 3D and also start registering this 3D data. So this is something we've been working on to find ways to use this really reliable 2D data to form it into 3D. Of course, there's a lot of ways to already do that, but most of the 3D models that are now available are either a lot of handwork or a lot of generalization. But since we have access to a lot of reliable 3D data, we want to comprise a method in which we can form that together into reliable 3D data. Well, you all know this this overview of different LODs in which we can draw, and basically LOD 0.3 is something we already have in the BGT. And looking from that, what we think we can do is create LOD 2.2 within DigiDialog BGT, so within our own base registration software, so that our users can actually use this data, which is reliable and correct. Because it's not about making nice images, as you all know. It's about generating correct and complete data. Our first solution was to use the AHN, or the height map of the Netherlands, to enrich the data we already had. You see here some data that was collected in 3D, or all the vertices for all the polygons you see here, they were collected in 3D. And in order to give the terrain a little more height and a little more life and likeliness to the real situation, we used AHN to improve this. And you see here a visualization in 3D from our own software. But there's much more that can be done than just doing this 2.5D thing. So we started talking with the 3D Geo Information Group from the TU Delft, specifically people who have worked on 3D Fire, to see if we can use the techniques behind 3D Fire to enrich our own data as well. Together we've worked on more solutions that are also based on 3D Fire. We tried focusing on buildings then, and specifically for buildings we came up with a solution that could help us map these 3D buildings and make them more reliable with more interesting and complex roof shapes. So we've come up with a whole lot of buildings and a whole lot of building types that we could think of, and see if these types of lines that we wanted to use would be enough to create this. Our conclusion was that what we need for buildings is the building footprints, which are already in the BGT, building contours from the BAG, which actually shows the top of each building, or the bird's eye view. We also want to map ridge lines, which can be measured with a lot of measurement devices, and specifically height jumps, so that we don't have to draw in vertical walls, but we can tell our software to focus that in. Also, slant lines is something we wanted to incorporate. From some of our customers, we got city GML 3D models that they already had. And using FME, we tried to combine that, and we actually analyzed the city GML model for these types of lines we wanted to find. And then these types of lines we would import into our own software. Some results that we've gained so far is first some separate drawings of different types of roof types that we could come up with, like you can see here. These are screenshots from our software for the 2D data and the 3D results. And these were our first building results we were really, really happy with already. An example you see here is a building in The Hague. And from the city GML model and the theory I just explained to you, this is the model that we could get. You can see it's still not fully complete, but it's already a lot more precise than what we had seen before that. This is another example of an interesting building. And what you see here is the result from this analysis from City GML. We also created a way to draw all these lines in our own software and then make 3D buildings out of it. So directly using the BGT as we're already registering it. So when we use that, this is what the result becomes. So there's a lot more precise data in that. There's a lot more detail that we can incorporate. And specifically for our end users, these type of things can be really, really interesting, because as you can see here, the ground surface of the building is much smaller than it was in the CityGML 3D model, because it's usually based on the BAG, so the outlines of the buildings. But focusing on the BGT, we really need also the way it is in the landscape. So we need to create complete, correct 3D, as you can see here. Some first results of some bigger areas you can see here. This is part of The Hague, close to the Holland Spoor train station. The landscape around the buildings is quite flat, but I can promise you it's still in 3D, what you see here. And all the buildings that you see here are created in the way I just explained. So we used CityGML, we sought for the specific types of lines we needed, and created 3D buildings with actual roof shapes from that. And what to me is specifically interesting, and what we're really proud of, is the round roof shapes that you can see on top of the train station. Then there's also some water boards we are in active contact with. What you can see here is a 3D visualization of a water measurement. And you can see that also in the profile that there's a lot of different height information that's incorporated in this model. And this is a lot of data, and we were just really glad to see that our software could take this. And you can see also in this example that the 3D model is really, really, truly based on triangulation and a lot of computation to attempt to make this a watertight model. There's still a lot of work to be done, but focusing on this reliable collection and editing within our BGT application, we think we can do a lot of interesting things with 3D. We also want to include some topological checks in 3D, but this is something we're still working on. And the models are only complete if we include all the surroundings, also the buildings, but also the civil engineering works like bridges and tunnels. We want the visualization to be clear. It doesn't have to be pretty or shiny, as long as it's correct. And then we want to be able to export all these correct 3D models. We've already come a long way, but there's still a lot of work to be done, and it's a really interesting process to be a part of. What I want to conclude with is that in these interesting times, Sweco is still actively searching for new employees, and you're very welcome to join us within the research we're doing for incorporating 3D in these base registrations, because not only us, but also our colleagues are really working on this, since the focus is more and more on correct and complete full data, so not only in 2D, but also in 3D. Also, we're right now developing a web application for the BGT instead of just the desktop application we have right now. So if you would be interested in some of this, or you would just like some more information, you can feel free to contact me or ask more questions about it.
Check. Well, this is a very nice presentation by Sweco. We have Fanny Strijer in the room, also a Geomatics graduate, and she can answer the questions that are raised by Laurens van Rijssel. The first question is, can this 3D model also be exported as TIN in an open format to be used for further analysis, especially the bridges and urban caves? Fanny, what do you think?
I think that an export functionality is really, really important. And the first export we made is actually a very basic format that just shows the vertices of the model. We're also trying to work on a CityGML export because a lot of our clients think that's very, very, very important. We also know that the format is so complex that we do not prefer this. Of course, we've also talked about a CityJSON export because, well, we've worked with the creators of CityJSON. But we really want to expand this functionality because we think it's very important, as our goal is to create really reliable data.
Super. Now we have well, not a question by Lines, but a question by Hugo Ledoux. The building on the pillars, was it created automatically from Bach BGT AHN3? Or did you do it manually?
What was created automatically was the footprint from GT because it's already there, and we added the Bach also automatically. The only things we had to add manually were the in between. But with the things we already have in place, a surveyor could go outside, just measure a few of these points, which is very easy for them, and then we would automatically have that in our software, and then it could be automatically created.
There you are. And then Dong Liang Peng asked this question: why is there a dense triangulation in the river? I think it unnecessarily increases the amount of data. Can you do without?
I totally agree. What happened here for this specific river, we got a measurement from a water board, and that measurement just contained a lot and a lot and a lot of points. What we wanted to do is simply use this measurement, this data, to create this 3D model for the river. Of course, before really storing it and exporting it, we would really thin out this data.
Okay, very good. Then a question for myself, and that's the last question for this part of the program. If you're looking at the videos we just had by students, especially the one of the Waterschapshuis, is that research or the research results, is that valuable for your data product?
It could be valuable. Most interesting for us is actually getting more reliable data as the basis for what we're creating. And in that sense, there could be different kind of ways where it could be very useful to help us actually add that and enrich what we've done. So, yeah, a lot of future in what we do. Yeah, fill the holes of what's known so far. Yeah.
Very good. Yeah, there is a grass machine mowing the grass just in, well, I'm not going to bother with you, bother you about this. Thank you very much, Fanny. If you want to join Fanny in the Sweco Discord, then please join her there. She will be there hopefully for the rest of the day. Maybe, yeah. Very good. Thank you very much. Then we continue the program with a break. Yes, we can take a coffee and go to the restroom, etc. And we will be back at 5 minutes before. No, at 3 o'clock exactly, with 3D noise simulation based on advanced input data using automatically generated tints. That's the group that's working on the project by RIVM and Rijkswaterstaat. So we will be back at 3 o'clock. Thank you very much. Yes, we're back. Welcome, Geomaticsday 2020. We're going to continue now with the video of the students of geomatics. The video is on the 3D noise simulation based on advanced input data using automatically generated TINs. And it's a project in collaboration with Rijkswaterstaat and RIVM. Mels, press the button and we can play the music. No, the video.
Welcome to the Synthesis project presentation of the 3D noise modeling team. Our team consists of Constantijn, Dennis, Laurens, Nadine and myself Marit. In collaboration with RIVM, Rijkswaterstaat and the TU Delft, we have developed a proof of concept to automatically extract a noise map directly from a triangulated irregular network, which is freely available. We have really liked this project and its outcome. We hope you do too. To model noise, a digital representation of the terrain is used. Currently, height lines are used to represent the terrain. These lines are three-dimensional lines representing high and low points in the terrain, not to be confused with isolines. These lines, however, partially require manual processing and are not as accurate as a tin. Our goal was to see if it was possible to directly use a tin representation of a digital terrain to find noise levels. Our hypothesis is that using a tin directly allows for automated 3D noise modeling according to the guidelines of Knossos EU. Nevertheless, this was never tested because existing software cannot take the tin as an input. In this presentation, we will first explain our inputs, how our algorithm works, then we present our results and discuss them in comparison with the current Dutch method. At last, we will go into the setbacks and limitations of our product and finally answer the research question. And now Laurens is going to talk about the algorithm.
Thank you, Marit. Our main input is the digital terrain model consisting of a triangle irregular network, also called a tin. Each 2D vertex has a height value and can therefore be lifted up to that height. As there can be only one vertex on a unique 2D location, vertical surfaces cannot exist. This is so-called 2.5D. We also use a building dataset of LOD level 1.2 or 1.3, which is based upon the BAG, building and address dataset. An LOD 1.3 means that a building can have different roof heights, however, the roofs are all flat. This buildings dataset is merged with a ground type dataset to provide semantic information to our tin. This data stores the material and the building height. The material can either be absorbing or reflecting. In order to simplify the process of getting a cross-section from the tin, we decided it was best to make the tin constrained to the buildings and the ground type polygons. During the project, this has become the replacement for the ground tin. At last, the algorithm also requires a set of roads, which represent noise sources, and a list of receivers, which represent the locations of interest. Our client requested us to use a method where we search for the intersection point between 2 km long rays coming from the receiver with a 2-degree interval and the road elements, as can be seen in the slide. The length of the rays is specified in the European Standard for Noise Modeling. Using these source-receiver pairs, we can find the different propagation paths, either direct or reflecting. For reflecting paths, our algorithm currently supports single reflection paths, also called first-order reflection paths. These are the most commonly found propagation paths and make up most of the noise. We have also developed second-order reflections, but the noise contribution did not overcome the increased running time. Therefore, we have not implemented it. The first-order reflections need to be validated. For that, we use two tests. The first test verifies that the size of the building is sufficient to actually cause a reflection. This is done by checking whether the rotating the ray by 1 degree in both directions still intersects the same building. When this is the case, the reflection has passed this test, as can be seen in the slide. The second test looks at the relative height in the case of buildings with common walls. The reflection is only valid when the reflecting building is at least 1 meter higher than the adjacent building, as can be seen on the right side. From these propagation paths, consisting of the source, receiver, and optionally the reflection point, we extract the cross-section by walking over the constrained tin. During this walk, we store the intersection points and add building roofs when encountering a building. This results in a vertical cross-section of the digital surface model, which consists not only of the terrain, but also the buildings. For each vertex, the material properties are stored. For one receiver, this is how these cross-sections look. As can be seen, a single receiver can create a lot of paths. Computing this for a grid of receivers quickly becomes computationally expensive. To make sure the computed paths are actually correct, we first visually checked whether the surface was accurately followed. From this side view, it can be clearly seen that the cross-sections follow the surface accurately. Secondly, we also tested the validity of the path with the noise computation software, which does several checks before computing the noise level. And now, Marit will talk about the quality of these results.
Thank you, Laurens. To verify the results of our method, we compare the results with those from our client. As this is to test to verify our concept, the client used the same input as much as possible. The terrain, buildings, ground types, sources, and receiver points are the same. We set up two scenarios, one with no reflections but significant height differences in the terrain, and another scenario with buildings and thus reflections. Let's start by comparing the scenario with no reflections. Looking at the images, they show that the noise results are very similar. There are three differences that we found between the noise results produced by EDVM and by us. First of all, our noise results showed more local minima and maxima, while the results produced by EDVM are more gradual. Besides, the noise results by EDVM showed lower noise levels further away, while our noise results showed lower noise levels in absorbing areas. Finally, our noise results are more prone to height differences. For a more quantitative comparison, a relative difference noise map and a histogram showing how each pixel in our approach deviates from the EDVM approach are shown. The majority of the pixels are within plus or minus 1 decibel from zero. This could mostly be attributed to the extra details provided by the tin. Now, let's compare the results when reflections are added. Both methods present the same distribution of sound levels. Both approaches also show noise contour lines pulled towards the buildings where reflections exist, which means higher noise levels near buildings. Looking at relative differences, we can see that in flat reflecting areas, the EDVM model tends to have a lower noise level as we get further away from the source. But in the absorbing areas, the tested method tends to generate lower noise levels. The histogram shows that the majority of pixels are within plus or minus 1 decibel from the 1.5 decibel. The only major difference between the two scenarios are the introduction of reflections. These reflections could lead to such differences since a longer distance is traveled in reflections and the details from the tin could finally add up and create higher noise levels. We use different files in order to extract the propagation paths. However, these files can have a difference in precision, which in some cases cause a reflection to become invalid. We have tried to solve this by adding a tolerance, but this did not yet solve it and caused other topological inconsistencies. Therefore, it is not solved at the moment. This will in some cases cause slight errors when using incompatible input datasets. It could be solved by aligning the precision of the input datasets. Also, creating a constrained tin, incorporating the ground types and buildings have proven to be a challenge in specific cases. This sometimes resulted in an invalid terrain, as can be seen on the right side. Secondly, in the algorithm we created, direct and first-order reflections are taken care of. The test Knossel software handles the propagation paths that are vertically diffracted. However, horizontally diffracted and multi-order reflected paths are not considered. At last, we currently only support roads as noise sources, but in reality there are many more noise sources. For example, railways, the industry and airplanes, which are not considered but can definitely contribute to noise pollution. We have successfully created noise maps, comparable to those produced by our clients, by directly using a TIN model of the terrain. We know how several of the differences are caused and how they could be solved. The concept is therefore proven to be an interesting alternative to the currently used height lines. The main challenge was to make the concept compatible with many different situations, which was successful in most cases. Further improvements to this concept are the performance improvement by implanting it in C. This will allow the concept to use the test Knassas functions directly and remove writing and reading many files to the disk. Secondly, include support for other noise sources, adapting to speed limits and amount of traffic. Besides, support for diffracting paths as well as multi-order reflection paths. And finally, expand the support for other ground-type materials. While working on this topic, we also noticed other possible improvements for noise maps in general. First of all, create support for higher level of detail of buildings that include slanted roofs. Secondly, support not only 2D, but also 3D noise maps for high rises in urban environments. Finally, support for vegetation. We have really enjoyed this project and we hope you enjoyed listening to it. Cheers!
Super, yes. Well, thank you very much, Group RIVM, for this very nice presentation. There are several questions popping up. The first question is by Balazs Dukaray from Delft University of Technology. The question is, you encountered several issues with the input data, especially considering the original set of input. If you were to fix the data, where would you begin?
First, I need to clarify something, that we have the input data that we got from for the project, and then we did something with the data to turn it into input data for our software, for our program. And the raw input data had invalid polygons. So first we needed to fix the invalid polygons. Sometimes polygons didn't have the value, so it had a value none of, let's say, like the building polygons would have a height of none, or it would have a roof level lower than the ground level, which meant it's an underground building. And we didn't need that for our program, so we had to clean that up as well. Or in the ground type data set, we had the polygons that didn't have an absorption index that we needed for the noise propagation. So that's the part with the raw input data. And then we had to overlap these data. And then we had the difference between the ground type and the building data set. And these differences gave sliver polygons or dangling segments, and that caused problems. And then we tried to fix them, but then we got a constraint TIN that had a different precision with the building data set. So we also have to change the precision of the building data set to match the precision of the new constrained TIN. So there were several things to fix for the input data.
Well, that's a very comprehensive answer to this question. We move on to the next question by Hugo. Did you interpolate the values, or did you calculate one value for each pixel? And then for the pixel, what resolution is this pixel?
Yes, the algorithm has as an output a set of points. We programmed them in such a way that there were a grid of receivers with a distance of 3 meters each from each other. So then we had to interpolate these values in order to get the map a continuous field. Among the two options that we have available in QGIS, we didn't program an algorithm for that. We used QGIS. We had a ID double and TIN. We first tested with ID double, but it had some problems, especially because we had to determine a search radius for that, and it was producing some artifacts. So we opted for the TIN, and the resolution was 0.1 meter for the raster pixel.
Very good. That answers all the questions. Next question by Jantien Stoter. also from Delft University of Technology. Do you think that thinning of the tin would be possible in a way that does decrease computation time, but without significant impact on the quality of the noise simulation results? Who can answer that question?
I guess I could. Yeah, it's either me or Nadine. I don't know. I do know that right now that's pretty much our biggest, like, is where the biggest computational part of our program is going into right now, and it does it is the main source of our accuracy over the previous method. So at least in what I remember. So I wouldn't say that it would be easy to take out a lot of the tin, and you wouldn't want to do that because that's something that the tin actually provides is quite a bit of high accuracy. But saying that, there definitely could be it could be used to, like, you could definitely remove some of the tin, but it would definitely impact accuracy. Like, it does come hand in hand, so I don't think it's an easy trade-off there.
Okay, someone wants to add to that, or is the answer? Very good. Then we move on to the question by Peter van Oostrom. I'll just do individual persons, and everybody can ask one question. And if we have time left, then we move on to the next from someone that already asked a question. So Peter van Oostrom asks, you mentioned noise level at higher locations, for example, 2 or 3D floor balconies. Any clues how this fits into your method?
Yeah, I can answer that. So in the cross sections that we produce, we write them to an XML file, which is then processed by the test Knossel software. And in that file, you can address at which height the receiver is placed on top of the local ground level. So normally we always do it at 2 meters height, which is the standard, but you can also set it at 6 meters or 10 meters height, and that will give you a different result.
Okay. Then a question by Jongliang Peng. Did you convert the tin to the noise map? Do all the pixels in the same triangle have the same noise value?
The conversion from the output, the points with the noise power values to the interpolation was actually the last part of our synthesis project, and it was meant to access the quality of the maps that we produced compared to the RPM one. So we didn't get into much detail about the interpolation technique. We just opted to the tin as it was producing better results for that specific purposes, and then we produced the comparison. We didn't focus that much on why was a specific interpolation method better than the other one. It is important to notice that we took this approach because we wanted to compare pixel per pixel. In the noise community, these noise values are often shown as contour lines and not as an interpolation map, but we decided to do that because of the comparison that we wanted to do.
Okay, thank you very much. Then we have a question by Clara Garcia Sanchez. You mentioned further work by extending from 2D noise prediction to 3D. Do you expect the propagation of noise to behave in vertical direction the same way as in horizontal direction?
Yeah, in general, the sound always the sound has a lot of different ways of propagating, and the good thing about horizontal propagation is that there's usually a ground terrain below it, which will actually cause multiple reflections. So the sound ray itself can go in many various ways, and if there is an underground below it, then it will have various reflections along that underground. But if you have a vertical path, that could also work. I'm not completely sure how TestKnossos deals that if you supply it in the same coordinate system. But for that, we would have to ask one of the clients. Maybe they can answer it in the chat. But I think it's possible.
Yes, and just to complement, we used as our main literature the Knossos guidelines, and according to the guidelines, there are three conditions that we can work with, which are homogeneous, favorable, and unfavorable. This third one, the unfavorable one, is the one that you can actually think of sound going from up and down, as in like not going horizontally, but actually working in 3D. And we didn't work with that at all. It was our main goal in the synthesis project was the proof of concept of if it was possible to work with the tin. So this was not the most important aspect for this project, but it could be conceived as further implementation.
So your supervisor from RIVM, I think, responded there as well. A question I have myself, because in this project, of course, it was on the scientific part, let's say, on a research topic. But can you also say something about the social impact of your research? If you could phrase it differently, who's going to benefit from your research?
Yeah. So every 5 years in the EU, every country is asked to produce noise maps for its country. And these noise maps are used for various reasons. It can be to find out whether you can build a building somewhere, or do you need a noise barrier to restrain the sound coming from a road. So but it's used for more purposes than only that. You can also think about, do you want to place a highway throughout a natural forest or national park? What kind of impact would that have on the national park? Also, things like that can be considered.
Interesting, yeah.
And if you think this theme is actually very interesting, because if you think of noise, you cannot visualize noise, nor you can touch noise, but it's still a very important factor in terms of the quality of the built environment. So I think that to answer your question, well, society in general gains a lot when you can actually map and access the quality of noise in our cities. And this is very useful for planning and urban design purposes.
Yes, fully agree. There's another question by Jantien Stoter. Let's take the second one. Let's say she posted on the chat in the chat. So, do you expect that adding more details to the building models, such as representation of roofs, LOD2, would indeed improve the results of the noise simulation?
The short answer is yeah. I'll say this real quick. The short answer is yes, it will. But the more complicated answer is that it will by such a small margin that it's probably not worth doing it, because when you're taking a look at an entire city, individual building facets are just not as relevant. If you're doing this on a small scale, then for sure. But on a citywide level, this is not a huge deal, unless you have big, outstanding like obstacles that have a major impact. But otherwise, no, not really.
Okay, so no improvement expected there. I get a final question by Jantien. You mentioned that no vegetation was considered. Is vegetation supported at all in the noise calculation methods? And if so, how is that being supported?
Yeah, it is supported in terms of material. So for each segment, so for each part in the cross section, you can supply it with a material, and there are 12 different default types of material, which go from raw asphalt, which is really reflecting, to very absorbing materials where they explain it can be considered like bushes or things like that. However, I believe it does not take into account for example, when you have trees, they are also quite tall. So they might be 10, 20 meters high, which also has another influence on the propagation there. And that is not taken into account. So the height of the vegetation cannot be added.
Okay, thank you very much. Well, that was the last question in the chat box. Let's say there's another question. That's a completely different question. But you work for a client or even two clients. How is that for you as students? That you were educated with some skills and competence in the geomatics program. A lot of theory was provided, but how is it working with the client? You're all silent now.
Well, maybe I can respond. Yeah, I think it was really nice. It was really clear to us. It really became clear to us that our clients, Arnoud Kok from RIVM and Rob and René from RIVM and Rijkswaterstaat, they really know a lot about noise and about how noise propagates and how to deal with certain situations. But on our side, so also our tutors, Jantien and Balas, they really know a lot about the data and the technical aspect of it. So that was a really nice match. And sometimes we had to explain something that was not completely clear to the clients, or how to implement that, or if something was easy, or if it would be really hard. But we could learn a lot from each other. So I think we all really enjoyed it.
Thank you very much. Well, I'll just see in the chat box I have to ask another question by Hugo, but let's make that one the last one. Wouldn't it be better to skip the tin and use a smart point cloud directly instead? A brief answer, please.
Well, I would say it depends on what the smart point cloud is, because we need to extract the cross sections, and we just, when we walk the tin, it's easier to know what is intersecting what. But when it's a point cloud, like if we miss a point, then how would we know what the cross section is? Or if we're missing an important building or something. So
yeah, so I think
that's a brief answer. Yeah.
As well as the ground level, it's really important to know that up to an accurate level. And you can use classified points, but still finding the right cross section in there, it has to be super fast, because as you could see in the presentation, there are lots of paths. Even for a small area of 100 by 100 meters, we already had more than 100,000 cross sections. So it's really important to be able to process these cross sections quickly. And for that, the tin was very efficient.
Well, and that was not the last question, because I also skipped the question of Balas. The focus of your project was on accuracy over computational efficiency. If you were to optimize your software, where would you begin? And that's really the last question, and then we move on.
Write it in C++.
Yeah.
Because like half of our program right now is outputting files. Like for every single cross section, there needs to be outputted a file which needs to be inputted into the Knossos software. So if you just simply write it in C, then you can instantly input it into the Knossos software without having to output to a file. There might be ways of doing this in Python. I'm not a Python expert. I'm sure there is ways for doing this. So we didn't do that. So if you remove something like that, then you're already pretty much reducing the program down to half its runtime currently.
Super. Point has been noted. Thank you very much. I will then be the only one giving you the applause for your very nice presentation or video and the discussion that we had. Thank you very much. And then we will continue in a minute with the presentation by Tensing, combining GIS and natural language processing. So again, thank you very much, and we will be back in a minute.
Good afternoon, everybody. It's nice to see you all here at the Geomaticsday. My name is Roland Mulmeester, and today I will be presenting on behalf of Tenzing what our innovative solution, geographic language processing, is. First, I will introduce myself a bit more, introduce what Tenzing is, and then we will change to geographic language processing, or GLP for short, which will be explained by my colleague Nick Jensen. So, my name is Roland Mulmeester. Actually, I graduated here in geomatics 1 year ago, and now I'm a GIS consultant at Tenzing. Tenzing is a GIS consultancy company, and our headquarters is in Waardenburg, which is in between Utrecht and Den Bosch. We are actually a subsidiary of Avinion, which is a bigger American company who is more specialized in geospatial data, where we, as Tenzing, are more specialized in GIS consultancy. We consist of about 65 consultants, and we're mostly specialized in FME and Esri products. Besides our specialization in GIS consultancy, we also have a branch which is called Tenzing Labs. And in this department we research technologies, new technologies, and create new and innovative products out of that. For example, we have the 3D Geo Viewer. That's a web browser based 3D data viewer in which you can import your building information models. We also have our Planet Object Detection platform, and this is a machine learning based platform which you can use to automatically recognize objects, for example solar panels, in aerial imagery. But today our main topic is geographic language processing, and geographic language processing, GLP, is a way to talk to your data. So that makes it able for non-GIS specialists to interact with your geospatial data. Nick Jensen is my colleague who created and researched this product, and he will explain you more about how GLP actually works. Nick, the floor is yours.
Thanks, Roland. Hi, everybody. As Roland said, I'm Nick Jensen, and I am a tech lead here at Tenzing. And over the past over a year, I've been working with GLP, or Geographic Language Processing, and trying to bring that to the market and develop it more. So as Roland described GLP, I want to talk more about the why, or how it works. And the main thing that we used as our mission statement for GLP is that with GLP, we wanted to enable non-GIS specialists to get answers to their spatial questions easily. So think of your grandmother or your mother, helping those folks get answers to their questions. It may be as simple as, where are the nearest fire hydrants to this school? Or I want to report this streetlight is broken in this location. Rather than them trying to figure out, okay, I need to do a buffer analysis, or I need to, figure out the exact latitude and longitude of this location, we want them to be able to use their own language to report such a thing. And that's what we try to accomplish with GLP. But more about what is inside of GLP, what's going on in there. So GLP is a mixture of GIS, which we're all familiar with, and then also natural language processing, or NLP. This is the technology that is used in Siri or Bixby or Google Home, any computer that is used to understand human language, whether it's being written or typed or spoken. It figures out what a user is saying and then sends a command to the computer, okay, the user wants this, do this. So we've taken those two technologies and mashed it together into geographic language processing. Now let's see GLP in action. We have a small demo here that explains it. What we have here is actually a web app from ArcGIS Enterprise, which is a system that you can host your own data in and create web maps with it. Additionally, you can also add widgets, which we've done here. And what we have here is a user who is looking at a sample water system for a city. And here we have the GLP Assistant widget. And within the widget, a user can start typing in what they're looking for. So right now we have a user who's not really familiar with the system, so they're typing in help me. And GLP, that chatbot in there, is saying this is what you can do in there. And here it says, all right, you could go searching for a project working area, and that's what this person has done. They've typed in PWA-1, and that has highlighted project working area 1. And then from there, they're looking to get more information about it. So they were looking for the description, which they got the description of it. And now they're looking for assets. So what are the pipes in there? What are the connections, the hydrants, the meters in there? So right now they're looking for the connection lines. And what has happened is GLP has highlighted, it's hard to see on this screen, but it's highlighted all these connection lines within this project working area. So, and then additionally, the user is trying to look for lead pipes because lead pipes are not good to have in a water system. So it has gone ahead and selected the lead pipes in this area. So this user can now write a report or send it out to the guys in the field saying, hey, you should go replace these pipes. And of course, they can select them. This is an interactive map that they can work with. Now, here they're typing in help because they're still not sure how to use it. And they're actually going to do or work with a function that is my favorite with GLP, and that is selecting something on a map and figuring out what it is. So they've hit select, and GLP has given them a select widget, and now they're going to select a project working area. And they tell GLP, I'm done, and GLP tells it, okay, you selected project working area 3. What else do you want to find out about this area? And they're going to look for distribution lines, and here it's selected a distribution line that runs through that project working area. Now, of course, this is using water data, but you can use this with any sort of data, any point, line, polygon data. We target the Esri ecosystem right now, so it has to be within the Esri format, but it could be country GDP, it could be fire hydrants, it could be roads, it could be bike lanes, anything. Doesn't matter what it is. But let's talk more about what's going on behind the scenes here. And what's the technical stuff here? So how does it work? What you saw there, that widget that was up in the corner, is what we call the GLP Assistant. And within GLP Assistant, that is where the user is typing things and receiving answers. And when a user types something, a JSON call gets sent to the GLP platform. And within the GLP platform, we have GIS and NLP working together. And when the GLP platform has determined this is, somebody wants some GIS functionality, it does a call out to ArcGIS Enterprise or ArcGIS Online, just a REST call, and gets some data back, brings it back, and makes an answer and sends it back to the GLP Assistant. Now within the GLP platform, there's a lot of artificial intelligence going on. So we have created several models that run in there, stories as we like to call them. And these stories help guide the user through the widget, what they're trying to accomplish. So let's talk more about the deployment options of GLP. We see GLP being used in 3 different groups: employees, suppliers, or the public. Public makes sense. It's anybody who's out there. You know, it could be constituents of a government or policymakers out there. Suppliers could be people who have access into an organization. Maybe it's a heating and cooling specialist or an IT specialist who's a consultant. And then employee is anybody within the business that is not familiar with GIS. So this is not for you guys, but this is for business leaders or other folks who don't quite understand GIS. And depending on these 3 groups, there's 2 different flavors of the GLP platform that we can put in there. The first one is GLP Online, and that works with ArcGIS Online. ArcGIS Online is another place provided by Esri that you could put your data there and be able to serve it up so people in the public can come look at it if you so desire. And we also have a GLP online platform that we can host GLP for organizations, and they can use the benefits of GLP along with that ArcGIS Online. The other flavor is GLP Enterprise. And that is GLP that can go behind your firewall, disconnected from the internet, and allows you to use your sensitive data within GLP while keeping it safe. And that integrates closely with ArcGIS Enterprise and also ArcGIS Online if you so desire. So to sum up, what, again, we're trying to accomplish with GLP is to enable non-GIS specialists to get answers to their spatial questions easily. This easily part is the hardest thing, and that's what we are trying to do with all our innovations here at Tenzing, is making things easier for GIS users and non-GIS users. And GLP is just a part of that. So thank you all for your time, and I'll turn the time back over to Roland.
Yes, thank you, Nick, for your very clear presentation about what GLP is and how it works. And I would like to thank you for watching our video of Tenzing. And now feel free to ask any questions in the chat about either GLP or Tenzing or what we do. Thank you all for watching.
Yeah. Super. Yes, thank you very much for your nice introduction to Tenzing and its activities. We have now here Roland Mulmeester and Nick Jans also in the room, ready to take some of your questions. And we have a question by Zhayu Sheng. How does the GLP platform differ from a natural language interface for geodatabases?
Well, if I understand the question correctly, GLP is simply trying to be an interface between your GIS data and NLP. So it's just trying to make it easier for users to interact with that data. It's not trying to replace natural language processing. That is not our purpose here, what we're trying to do, but rather we are just trying to add in an extra component on top of natural language processing, NLP.
It's very clear. And then another question is it just in Dutch or is it also available in English? Or what languages do you support?
Yeah, we support all the major languages of the world, including Dutch. So we use some already existing natural language processing technology out there. So others have gone out and incorporated the major languages, French, German, possibly Chinese, but definitely Dutch and English and Spanish, the big ones.
Interesting. Yeah, I have also a question because you say you're focusing in the GLP on, let's say, the non-GIS specialist. Does that also include the citizen, or is that a special kind of species, let's say?
Yeah, definitely. This is built directly for citizens. Anybody who doesn't understand GIS. So it could be your mother. It could be a citizen in a city. It could be office users who don't use GIS every day. We're trying to get anybody who doesn't understand what a clip, buffer, layers, geodatabase, all that stuff. We're trying to help out those people.
Okay, well, to me it looked a little bit complex for my mother, but we'll have to see how she works with that. If she's going to work with it. I don't see any other questions. Maybe a final question. Student work. Do you also have, let's say, internship, graduate projects? Is that also possible in Tenzing?
Yeah, that's also possible here. We have all kinds of different projects going on in Tenzing right now. So yeah, with this project or with many others, we can always use an extra hand.
Super. Well, students, if you would like to do something with Tensing, please join them in the Discord channel and inform yourself and make yourself known to them. For now, thank you very much for your presentation. We will continue with the next presentation or video in this full program. This will be the presentation on the point cloud deployment for fire fighting strategy. We're going to look into HoloLenses. Mels, I think you can press the button.
Our project is about the deployment of indoor point clouds for firefighting strategy. This geometric synthesis project is executed by Charalampos Babis Gatsidiakos, Jos Veenstra, Ruben Hurkmans, Max van Schendel, and Camille Morligem. Our clients are CGI and the Safety Region of Rotterdam, represented by Rob Wachaar and Huip Franse. Our supervisors from the TU Delft are Edward Verbree and Robert Wouten. Imagine a team of firefighters being called to fight a fire inside of a building. This is called the alert phase of an emergency response. They hurry over to their fire truck and go to the location of the incident within the en route phase. Once arrived, they equip their protective suits and start exploring the emergency site to gather as much information as possible. This is called the exploration phase. The information gathered within this phase includes the building's characteristics, the nature of the incident, and the location of the fire. This information is essential to determine which strategy they use to fight the fire and to rescue whoever is inside. The person responsible for defining these strategies is the incident commander. The incident commander supervises and interacts with the team remotely. Despite the high stakes and stressful conditions of a fire, the commander has to be able to make important decisions in the nick of time. However, the commander does not have visual feedback on what is going on inside a building, and a wrong decision might lead to decreased effectiveness or even casualties. Besides the overarching strategy, firefighters also need to take decisions within a limited time frame. Situations that the strategy has not taken into account are bound to happen, and when they do, how the firefighter responds may mean the difference between life or death. When making split-second decisions, it's not just the amount of information that matters, but also how quickly and easily you can access it. To provide the fire response team with the information they need, when they need it, we created Incident Mapper. Incident Mapper is a real-time collaborative information system which can collect, process, and distribute information about the scene of an incident and the people involved in the emergency response. The system consists of two modules, the Explorer and the Navigator. The first module, the Explorer, is used by firefighters in the field. It tracks the user's position inside of the building while simultaneously creating a 3D map of their environment. It also allows its users to manually add information to the environment and to view it using a head-mounted augmented reality display. The other module, the Navigator, is used by the commander of the response team. Its main purpose is to dynamically combine information from multiple explorers into a single model in real time. The Navigator also allows its user to view the model in different ways, to interact with it, and to distribute information among the explorers. By supporting the feedback loop of gathering information, making decisions, and taking actions, Incident Mapper could make fire response teams more effective and reduce the risk of field operations. The first component of the Incident Mapper to be discussed is the Explorer. The Explorer makes use of a head-mounted device called the Microsoft HoloLens, which continuously captures its environment and records its positions relative to it. This data is recorded relative to the HoloLens starting position. This is problematic because we want to combine data from multiple explorers that each have a different starting point. To solve this, we used a method called spatial anchors. A spatial anchor essentially serves as a common reference point which can be recognized by multiple HoloLenses. It works similarly to how humans describe the position of an object or of themselves relative to a landmark. as we could indicate the position of a bus stop by saying the bus stop is 100 meters to the left of the statue, multiple explorers can describe their position and environment relative to a spatial anchor. By projecting light onto an internal display in front of the user's eyes, the HoloLens can also overlay virtual objects called holograms onto the real world. This means we can show information to the user in a way that does not interfere with their work. By performing a pinching gesture, the user can summon a menu in which spatial markers can be chosen and placed in the environment as holograms. This menu can also be used to place spatial anchors and to toggle the lifeline. When the lifeline is toggled, the line connecting the user's position over time is displayed. If the user loses their way during a deployment, they can simply follow the lifeline back to where they came from. The display also contains a minimap in which the position and orientation of the firefighter is shown, as well as the position of objects in the scene, which can be used to get a quick overview of the scene itself. The Navigator application acts and serves as a centralized hub or cloud. It can send, receive, store, classify, and visualize spatial data. It also offers a UI to control how it is used, to look at the data, and to interact with it if it is being captured in real time. The Navigator is meant to be used by a commander or other supervisor and shows an overview of all data currently being captured by all personnel in the field. It also shows the position of these explorers, and it offers ways to interact with them using position-based commands. Explorers capture their surroundings directly as meshes. The Navigator platform offers different ways to view this continuous stream of meshes. The model can be visualized as a point cloud by only showing the vertices. This is useful for overlaying multiple different datasets. Another visualization is a transparent wireframe mesh. This makes the surfaces more readable without obstructing other meshes. Thirdly, the Navigator offers fading visuals by giving meshes an expiration date. A mesh previously sent might not be accurate anymore if, for instance, a car has moved or if a wall has collapsed. Lastly, the Navigator can show how the meshes are classified as a floor, wall, ceiling, or a piece of furniture. The Navigator is able to track and receive data from multiple explorers at once. This allows the user to get an accurate overview of the position of personnel. By distributing the position data back to explorers, they can track other explorers in augmented reality, even allowing them to see where other people are through the walls. The main reason for which real-time capturing and visualizing data is needed is to directly make the data usable as a means of communication in the field. A simple way to do this is by creating and sending spatial markers. These can be added into the Navigator environment, which is then automatically synchronized to the explorers. Using the markers, the incident commander can signal the positions of objectives to go to or calamities to stay away from. This project can serve as a baseline for multiple other research topics. A first research topic could use contextual data as a starting point. Integrating the indoor 3D model within the external shell of buildings by using GPS would put the model in a much broader context. The second research topic is sensor fusion. This research topic should not focus only on HoloLens or even on mixed reality devices in general, but also research should be done on utilizing any other external type of sensor, such as thermal sensors, smoke detectors, Wi-Fi, or conventional LiDAR sensors, which could massively improve the functionality. Robotic substitutes like drones or terrestrial scanners could replace firefighters in situations where exploration is dangerous. Bringing multiple datasets, like the ones generated by a single HoloLens, within the same coordinate system gives us the ability to overlap the layers. What would be even better is one integral model, instead of several separate layers. The last research topic is immersive user experience. In this project, we have only scratched the surface of the possibilities the broad field of extended reality can have on using and experiencing datasets. For example, the navigator can also run on a HoloLens for a more immersive experience of the data gathered. Thank you for your attention.
Thanks. Thank you. Great. Yes, you're muted, Bastian.
Sorry, I was muted, so that explains why I was so late in this meeting. Thank you very much, team. It's very interesting presentation, but we also have some interesting questions. Let's start with a question of your supervisor, Edward Fabre. First one, if you in your video you don't show semantics like the wall, floor, doors along the geometry, but you did so during your project, what is more important, detailed geometry, meshes, or less points with all deep learned semantics attached to them in real time?
Yeah, that's basically two questions. Babis, why don't you answer the first one? So what did we do with the semantics?
Yeah, first of all, maybe you can stream your screen, and Camille can talk about the classification, and I will talk about the more complex semantics, which is explored in details in the report. We can show it really briefly what we did. Camille, you can start with the classification if you want. And you are muted. I don't know if you see.
So we implemented the classification algorithm. So basically, the HoloLens they gather meshes, and we basically use we compute some properties of those meshes, like the minimum 8, the maximum 8, or the average area. And based on that, we compare those with thresholds, and we can determine if the surface of the meshes is either the floor or a wall surfaces or the ground. And I cannot see the screen because my computer is loading, but it's possible also to show only some parts of the meshes. So you could choose to show only the walls in the navigator, or to show only the ground, and that way it can help the firefighters to have a better understanding of the indoor space.
Yes, and to answer the second question.
To add also, sorry, something to the semantics part, I can say about another functionality that is linked to semantics, about the more complex semantics, the door detection. As you can see here in the example, I won't go much in details how we detect the door. Basically, it's intersection between wall planes and line segments that created from the trail of the user with the HoloLenses. As you can see in that room, the door is detected. We implement that algorithm to add more complex semantics. It's important to mention that in order a door to be detected, there are two requirements. So yeah, firstly, the walls next to the door should be scanned properly, and secondly, the user have to pass through the door and not just to scan the door. But yeah, we find that this can be useful to firefighters, this knowledge before entering a building. So that's about semantics.
And the second part of that question was about what's better, basically a lot of data points, or maybe just like a point cloud of data, or do you want to dense that down to just some key points? And as most of these questions, the quick answer is it depends. Because, for example, you also run the risks, always run the risk with classification algorithms that it's not properly classified. Plus, it costs computation time. So it's a balancing act between giving clearer information, because this is clearly a lot harder to read in one glance than maybe just a let's say a classified point cloud where we turn the furniture off. But yeah, if you want that more complicated or more high-level abstraction like that, you run the risk of not classifying things properly, so weird glitches, and yeah, a larger computation time, so a larger time between the response team doing something and the commander reacting to it.
Okay, thank you very much. Edward had another question, and that is on this Boston Dynamics spot dog. Basically, the question is, can it replace a real person, the real firefighter?
Can I answer this question?
Of course you can.
Well, the situations where we imagine such a robot could be used is as the absolute first responder, the first person to enter a building. And although they might not completely replace humans, they don't have the ability to improvise like humans do, they could be a good replacement to get a first overview situation, which is the most dangerous part of the deployment, the first person to enter, and then transfer this information to other firefighters. So not a replacement, but an improvement in some situations.
Okay. Very glad to hear that we're still useful as human beings. Then Lawrence has a question. Do you know how these spatial anchors are found and matched?
Yes, so they are not found. We create them manually. You can indicate the position. And basically what a spatial anchor contains is a point cloud, which is scanned by the HoloLens, and a collection of other sensors, such as the camera feed of the HoloLens, and it also contains the Wi-Fi fingerprint of the current location of the HoloLens. And all of this data together can be used to match the current position of a HoloLens to the description of the spatial anchor. This is all proprietary, but we can, in our report, we discuss several methods which they can use to, for example, match point clouds independent of rotation and translation.
I think that answers the question. And a question by Ravi Peters, a more practical one. Well, this HoloLens is quite critical, but does it still work when there is a lot of smoke in the building?
I can answer the question. So it doesn't work with dense smoke, but yeah, with maybe sparse smoke it works, but not with dense.
Although it should be mentioned that this is a few years old at this point, and future iterations of the HoloLens could improve this.
This is still a big practical obstacle to use for firefighters, I would say.
Yes, certainly. And, this project is just a prototype, but it still depends on some technological improvements before it can actually be used in the field.
Clear. Okay, then Maarten de Jong asks, what kind of GPU is required to visualize this data in real time?
Just a regular one. It runs a laptop on Jos's computer, so it's no.
Can I?
Sorry.
Yeah.
Please answer one at a time. Yeah.
Yeah. Sorry. But you don't need an advanced system. This can be built and run on a tablet. So you don't need. Although we built this thing inside of the Unity platform, which is primarily a game engine, it's not heavy at all. So I hope that answers it.
Okay. Yeah, that's also the other question: how far is data simplified to keep it fast enough? There is no need to simplify it. Huh? Okay, then Peter van Ozem asked, was all data that you showed in your video collected by yourself?
Yes. In the video, yes, but the streaming that we did now, it was a CGI room, so it was message that was provided to us and not data that we collected. But we performed an actually testing, like not all of us could attend due to the current situation. We are in different countries, some of us, but the guys went to the library, so yeah, the data are from there.
Okay. Very good. Then we have someone in disguise, RCBNL. What is the range of the explorers starting from a mutual cloud anchor?
Well, we haven't been able to quantify this exactly, but we were able to at least move around the entire TU Delft library without losing tracking. Although, and Lawrence asked another question about this, the accuracy does remove the further, we only use one spatial anchor, and the accuracy does reduce the further you move away from one.
So a proper future implementation would, although we only need one, it's like the usual. What usually happens when you try to merge two point clouds together, for example, you want an overshoot of matching data so you can do some least square adjustments. So yeah, that would be the next step. Yeah.
Okay, then the same RCBNL asks, can cloud anchors be linked to GPS points in real time so that indoor positional data can be streamed to the currently used applications?
Yes, they most certainly can.
Can you explain a little bit further?
The HoloLens doesn't have a GPS sensor, but the Azure Spatial Anchor service that we use also allows GPS to be added to the blob of data that the spatial anchor consists of.
Okay. Then Dongyang Peng asked the question, if someone is running, like firefighter is running in the building, is then the system still fast enough to visualize the data of the surroundings?
Yeah, we did a lot of tests about like the reliability on the system under stress. We didn't want to use a like €3,000 tool provided by us by CGI. We didn't want to do too crazy things with it, so we kept it. We didn't use it in smoke to test the smoke range for ourselves, for example. But we did try to move as fast as possible with the system. I've got some data sets I could show them, but the range, as you might see, is very limited. It's about the cone you can see right here. But you can move quite fast if it has enough pre-acquired tracking points. If you move really fast into an unknown direction, without any prior exploration, it will lose tracking.
Although it can regain tracking.
Yep.
Okay, there's some care, some work to do there. Then Geomaticsday, whoever that is, asks, what is the risk of a firefighter truly trusting these kind of applications? Which parts can safely be used, are accurate enough, and which ones should be used with some special care? Can the firefighter trust the system?
These sorts of questions are hard to answer in a yes or no way. But what we can say is that we put a lot of extra efforts on the reliability of the system. And for example, when you try to communicate, so the explorers map their environments, they send their meshes through the Azure cloud system back to the navigator. And we made several fail-safes in that whole system that if a small piece of the puzzle was not loaded properly, it could be added quite easily, a sort of chunk loading system, as it were. So I think the reliability aspect is something that can be best addressed by just the coders themselves. So the features must be implemented in a way that that there are several like fail-safes to go back on. But in general, the meshes scanned by the HoloLens are already very much a pre-filtered, and from what we've seen, because it's a proprietary closed system, from what we've seen, they're insanely reliable, albeit very limited. So I would trust those things. I would really trust the just the HoloLens by itself. In a merger, we might, for this to be actually used in a real life situation, it would be really great in a future iteration of the same exercise that there would be some sort of check happening from multiple sources. Is this data the same as what 3 other HoloLenses are seeing right now? So to get some confirmation in the system, that would be really nice.
That's on the input side, and that you also look at the consequences for the let's say the job description of a firefighter. Does the use of this application require intense training, or can you use it right from the shelf?
Max, maybe you want to get into that?
We try to design it to be as non-intrusive as possible, so to be able to be used with hand gestures and stuff like the mini-map. We try to make it as simple and because firefighters don't have time to look at a lot of things in the field, they want to be able to see stuff right away. This is really something we set as a goal from the start to assist the firefighters and not impede them.
The non-GIS experts should be able to use the system right away.
It takes a bit of getting used to the HoloLens and the hand gestures, but it should be usable by mostly anyone.
Very good. Then a suggestion by Robert Fout. Would it be useful to give different floors different colors to be the of assistant of the firefighter?
Yes, and that can be done. By the classification algorithm, multiple floors are detected, and things like ceilings and floors are classified in that way. So yes, that could be the very next step. There are also shaders for point clouds that basically do the same thing. This would even we don't even have to do a classification for that. The points can just be shaded like that, so that would even be more reliable. So yeah, there are definitely options. Yeah,
that's an advice for our architects for the inside interior ones, focusing on designing nice colors in buildings. Okay, then a question by Peter van Oostum: is the HoloLens 100% based on imagery, or are other sensor types used, like sound, radar, passing through the smoke?
I'll answer that. It is based on a time of flight depth sensor and 2 RGB cameras, and it has a Wi-Fi sensor. But no, it does not use radar, but or other sensors. But in the future, it could be. We didn't imagine this project to run purely on the HoloLens. It could be integrated with more sensors. It doesn't have to rely all on the HoloLens.
Okay.
Very good.
Then a final question that I have, and then we move on to the next part in the program. So in your report and also in your presentation, you highlight that the network has to be trained, and the training machine is often, let's say, unique. So there is a big difference between training the network for a train station and one for the hospital, and maybe also the hospitals differ a lot in between. Does this imply that the further implementation is still a long way to go?
I think you're confusing our project with the point cloud projects.
Oh, is it?
Implementing the deep learning algorithm. This does not need prior training.
This is the wrong. Okay, I'm sorry for this.
But but it's a nice segue into. I think it's really interesting to look into merging these 2 projects, especially so the project done for the NS, because if they manage to train a point cloud on just really general buildings, if they get a fairly accurate, fairly reliable classifier in there, and if it runs on one of these chunks of a mesh in near real time, it could be implemented, and then you would get a much more general classification algorithm based on deep learning inside of this tool. So it could, the interaction is possible. I just wanted to add that in there.
Super, yeah. Well, all the projects are connected in the end, I guess. Okay, thank you very much. Big applause for you as well.
Thank you.
Of course, the rest will join you. Then we will continue with a presentation by Fugro, creating a safe and livable world through smart monitoring of urban infrastructure. Mels, you can press the button.
I'm Robert Hollebach. I've been working in this company for 13 years. I pretty much grew up in this company. I've been in different managerial roles in 3 different countries. And I'm proud to be the Global Business Line Director of Land Asset Integrity at this moment in time. It's all about the landscape of our clients and how they are coping with the challenges that they have with aging assets and retiring employees, and how we contribute with our geodata solutions to support them in facing those challenges. Land asset integrity covers the sectors of energy and infrastructure. We specifically work for utilities, railroad companies and road authorities, but also for processing environments and refineries. We reinvented ourselves from a commodity business 5 years ago to a solution-driven business now. Most prominent in that is Roam's acquisition and Roam's technology, which makes use of the latest and greatest technologies in machine learning and remote sensing technologies. Utilities are faced with an existential challenge. They're confronted with energy transition, and it means that their network and the distribution networks need to be changed and need to alter to the demands of the future. And what Roam's does is provide a baseline for a grid modernization program. On top of that, it mitigates bushfires by understanding how forest and vegetation is encroaching on the network. We support transport networks, for example, with our ARAN and RILA technology. When we use our ARAN technology on roads, that road will be safer, that road will be fuel efficient. Also on the RILA side, we are reducing the amount of people that we need in the rail corridor, thus increasing the safety, but also reducing the disruptions to the community. The future of the land asset integrity business is dependent on how our clients are dealing with maintaining and repairing their critical infrastructure. This is true for established economies, but also in emerging economies like India, we see that need developing at the moment. It's all about how we mature our digital asset management solutions together with our clients to eventually become the geodata specialist for asset owners and operators.
In this section, we would like to introduce RILA to you. RILA is short for Rail Infrastructure Alignment Acquisition System. Please watch the introduction video.
Fugro Rail Data provides essential infrastructure information for rail professionals. We help to build a better understanding of existing rail assets to optimize your planning, design, construction, and maintenance of infrastructure. Our unique Rail Infrastructure Alignment Acquisition Platform, RILA, is a safe, fast, and affordable way of delivering accurate, up-to-date information and analysis with no disruption to train service. RILA provides millimeter accuracies in measuring absolute track position, track geometry, and the wider rail corridor above and below the subsurface. Creating the ultimate form of geointelligence, Fugro Rail Data is bringing the 3D railway environment to your desktop. Value inputs and financial returns of survey data become more evident in rail asset management. A constant supply of accurate, reliable data improves decision-making, all without disruption to train services and without the need to send staff on or near the track. Information is delivered to our clients via our web-based RILA portal, where clients can remotely view, inspect and analyze assets and provide inputs to asset management and engineering operations. Rail engineers use our 3D information to gain insight about all relevant rail infrastructure assets. This enables accurate work preparation and design decisions based on up-to-date data. This improves safety and efficiency, leading to higher quality work with faster delivery times. Fugro Rail Data provides the smart technology and logistics solution that can power your rail asset management systems with accurate, up-to-date rail infrastructure and geotechnical information with no disruption to train service.
The products of RILA are track position, track geometry and condition, 3D point clouds, and so on. Let's have a look at an example of track geometry and condition monitoring. In the project Amsterdam to Eindhoven, we measure the track geometry every month, mounted on passenger trains. The results shown here is the track quality. The horizontal axis is the mileage, and the vertical is the time from old to new. The track quality value is based on the standard deviation of track longitudinal level and color-coded. The red color indicating poor quality and the blue indicating good. Here we see the track at 20.7 degraded from August to November 2018 until a maintenance performed in December 2018. After that, the track kept stable. However, the track at 21.9 was also maintained in December 2018. However, it kept degrading and became even worse after 1 year of maintenance. Also, we can analyze how track degrades in the whole section. Here, we see 2 times of track maintenance, but which one is better? This is the maintenance evaluation. And how will the track degrade in the future? This is the degradation prediction. Both of them are crucial questions for track owners like ProRail. The track degradation algorithm will be studied using machine learning method by Karim, who is a master student from TU Delft, starting his internship at Fugro this August.
In the next section, we would like to introduce you to Symmetry, a versatile, user-friendly 3D data visualization and analysis platform. At Fugro, we have already been using Symmetry in various ways to serve our clients, for instance by supporting them with their emergency management services. Symmetry started because a large majority of our clients in land asset integrity had the same primary pain points. They had various data types in disparate platforms. They lacked proper communication channels to reach the public, teams had limited access to data, and a synced system to collaborate utilizing the data did not exist. How could we address this need? Our clients routinely have a lot of big data, and nearly a quarter of them leave it sitting on the shelf. But if they had the data managed properly, they could rely on it to make better decisions. And so Symmetry was born. What is Symmetry? It's a 3D modeling platform designed for GIS-enabled data management, visualization, and communications. With Symmetry, we're moving beyond the traditional pixels, stats, and graphs. We are providing a 3D ecosystem for GIS-related analysis with all available data sources in a single platform. Because Symmetry is intuitive, both novice and skilled users can make more informed decisions, better manage their assets, and protect life. Now let's show some examples how we use Symmetry to support our clients with their emergency response services. To test the static water level rise, we created a flood event around the city of Austin, Texas, and compared this against the 100 and 500 year floodplain model. Our simulation matched nicely with the flood limits provided by FEMA. The flood simulation in Symmetry works nicely with the existing LiDAR data and 3D models for displaying the impact this flood will have on the environment and community. A future Symmetry development would be to utilize the water level tool connected to tide of flood gauges for real-time water level simulations. The fire response simulation provides a meaningful representation of a fire scenario. This provides a platform for planning and training of emergency response situations and the time it would take to respond to that event. Here you see a simulation of a building fire where we can include smoke, and then we've added weather conditions so you can see the directions of the smoke. In this video, we show how we can simulate the time it would take for an emergency vehicle to leave the fire station, travel a specific route at a predetermined speed, and the amount of time it would take to respond. The responders consider this while planning city events where street closures may be required. The collapse zone tool was created to assist first responders with simulating a structural collapse or help with decision-making during a fire. The tool was created while observing a report of a building fire in Washington, D.C., where the responders needed to set a perimeter of 1.5 times the height of the building in case it collapses. Our developers were able to quickly create this tool to help identify the roads to close, the neighboring property owners to alert, and the first responders to identify safe areas for response personnel staging. The floor plan tool was developed by Fugro as a solution for emergency responders to easily connect interior information with 3D models. When complex interior scans aren't available, Symmetry can easily connect to simple drawings to help with situational awareness, planning, or response. The tool allows the user to select a building footprint or create a building outline, identify the number of floors both above and below ground, create the floors, and attach PDFs to each floor. Symmetry allows for easy interaction with datasets that include interior scans, building design files, or building information models. Within Symmetry, the user can seamlessly move from the exterior to the interior and use the walk mode to navigate down hallways. Hopefully, this introduction provided you with some insights in how we at Fugro use Symmetry, a versatile, user-friendly 3D data visualization and analysis platform, to provide our clients with insights into their 3D geodata.
Super. Well, that was also an impressive video by Fugro. We'll have here 3 people from Fugro. We have Justin, Stefan, and Wouter that are ready to take your questions. If there are any questions in the chat box, please. Yes, there we are. Peter van Oostum, a professor in our university, is asking the question. In Ryla, the data sets also are temporal, repeated scans. How is this used for change detection, deformations, for example, given a large volume of the data, including the point clouds? Is the question clear?
Yes.
And who can answer the question?
Yeah, actually, Symmetry does have some capability to measure things temporally. And with that, we even use it for shadow analysis and everything else, where you can take a presentation and scan it over several days, and you can see how things change. You can present it that way. And such like that. We use that a little bit for shadow analysis. So you can see, for example, how a city would look in the morning versus evening. Sometimes we'll do that for verifying things, where you can verify things like whether a solar panel will get enough sunlight at certain parts of the day, things like that. But it does have that capability. We haven't really used it very much, and we're looking forward to other ways where it can be applied. Does that help with the answer?
Yeah, well, thank you very much.
That's. I think that's for Symmetry.
Yeah.
For Ryla, so that's specifically for the real. What we do is we take repeated scans, usually over several months. So the one that we showed from Eindhoven, it's taken over several months, and these point clouds are all stored in the cloud, let's say. So we deliver them on hard drives, we put them in the cloud, and then we process those. And then what we in the end get is per track, per kilometer, let's say. We eventually get a height of where this track is, and then we can we look at a specific piece, say 50 meters, and then we look at standard deviation of the height, and then we can see if it deviates quite a bit. So it's what you saw in the graphs. That's a measurement of how smooth the track is, let's say. So if in these measurements, if the entire track would be lifted, you would not see it. But if it is sort of like a bumpy, rough track, let's say, then that will show in the measurements. And yeah, so and the key is storing this data in the cloud and making it easy accessible that way, that you can quickly retrieve it. But it's the measurements we derive from the so we don't go back to the raw data every time. We save the intermediate results. So it's one time it's a big computation, and the second time it's you use the derived already results and you compare those to the subsequent measurements, let's say.
Okay, very, very good. Well, time is almost running out, but I do have one more question. If there is a student interested in doing an internship or a graduation project for you, what would be your #1 project topic?
Point cloud classification. That one is really big right now. And also image feature extraction from images is also getting big. So we're always looking for people who are interested in analytics and machine learning to help us out.
Okay, thank you very much, students. If you are interested, just join the Fugro channel on Discord and make yourself known to Fugro. I hope you will be around for a couple of more minutes, that students are able to contact you, or maybe even later in the online drinks. But for now, thank you very much, Fugro. We will continue with the program, and we move on to the final student presentation, which is by 52. No, it's not by 52 Impact. It's the students that worked for the project Commands by 52 Impact. And the project was now entitled A Strategic Approach for Site Selection of Waste Facilities in Mexico. Mels, the floor is yours. Well, at least you can press the button to move to the video. Thank you very much.
Produced in Mexico every year. In Mexico, more than 53 million tons of municipal solid waste is produced in Mexico every year. In Mexico City alone, over 20,000 tons of waste is produced every day, which is enough to fill the country's largest stadium within a week. To worsen the waste problem, a lack of proper waste management services leads to the open dumping of waste. The World Bank estimates that 21% of all municipal solid waste in Mexico ends up in open dump sites. However, the former Mexican Secretary of the Environment suggests that this percentage is actually closer to 70%. The practice of open dumping pollutes the environment, which also has negative impacts on public health. For this reason, it is important that the amount of open dumps in Mexico is reduced, and that investment in new waste facilities is made. Therefore, our synthesis project is focused on developing a strategic approach for site selection of waste facilities in Mexico. We worked together on this project with our client 52 Impact and supervisors Edward Verbrey and Bastiaan van Lunen.
Hello, my name is Maurits. I work at 52 Impact, a company based in Rotterdam, where we use satellite data technology to monitor what's going on in the region and use that information to help businesses become more sustainable. In the last couple of weeks, we had the fortune to work with 6 very dedicated students on a project for one of our clients, a beverage company based in Mexico that aims to reduce their waste production and the impact waste has on the environment.
Based on the task provided by 52 Impact, we formulated the following research question. What are the weak spots in the current waste infrastructure network in Mexico? And based on this, where should strategic investment be made to improve waste disposal? First, let's start with a small background to waste management in Mexico.
In Mexico, municipal governments are responsible for the collection, transport, and final disposal of municipal solid waste, which is waste generated by households, offices, markets, and other non-industrial sources. 84% of the Mexicans have access to waste collection services. This percentage varies from state to state and is the lowest in the southern regions of the country. To stop the illegal methods of waste disposal, waste collection services should be improved. Also, the open dumps, which are currently the majority of waste disposal sites, should be closed and replaced by sanitary landfills to reduce the impact on the environment and the public health. An important aspect of constructing a sanitary landfill is selecting the most suitable location for the waste facility.
This leads us to our research approach, which aims to find the best place for investment in new waste facilities. It consists of 2 parts. Firstly, we start by determining the weak spots in the current waste disposal infrastructure. Then, we focus on the weak spots in more detail and develop a spatial decision support system to select suitable locations for new sanitary landfills. We will now explain each part of our methodology in more detail, starting with the weak spot detection.
What is weak spot?
Which spot is region that should be prioritized in waste infrastructure improvement and investment. To detect which spot, we first collect relevant data and split them into two groups, direct and indirect factors. Direct factors relate directly to the waste problem. For example, the capacity of sanitary landfills and the waste collection rate. Indirect factors might relate to the waste problem. They are mostly socio-economic factors, for example, population density and poverty rate. We perform spatial analysis on the direct factors to study the spatial distribution of waste facilities and the relationship with the waste disposal sources in Mexico. Then, we perform statistical analysis to determine which indirect factors were related to the waste problem. One of our findings was that the gap between the total amount of disposed waste and the capacity of the sanitary landfills is quite large, and the areas of deficiency spread throughout the country. Therefore, using this factor alone cannot strategically detect the prioritized spot for investment. On the other hand, the indirect factors showed an interesting link between the lack of proper waste management in the rural areas and poor areas in general.
The data sets of direct and indirect factors were then normalized to a range from 0 to 1. And as a last step, we checked the data sets for multicollinearity by calculating the variance inflation factor between any two factors. We checked which two factors show a VIF higher than 4 and then removed one of the two factors. This is done in order to take care of redundancy. For example, the percentage of illegal disposal has a very strong correlation with the percentage of people with access to a waste facility, so we cross one of the two out. From the refined set of factors, we grouped them according to 3 scenarios and performed a weighted overlay method to produce the maps. In the first scenario, we add up all the normalized values of the directly related factors only and use equal weighting for all factors. The second scenario, we do the same for the indirectly related factors. This map could be of use if there is little data about waste management available and can tell us more about the characteristics of weak spots. The third scenario focuses on factors that are suitable for landfill investment. Since landfills generally work better in densely populated areas, we add more weight to those factors. The map of the first scenario is used as the input for the selection of potential locations of new landfills. Areas with the lowest score are detected as weak spots. The weakest spots in the current waste disposal infrastructure of Mexico are located in the south, mainly in the state of Oaxaca, which is one of the poorest states.
After we got the result of the weak spot from the previous step, then it comes to the second part of our methodology. The aim of this part is to find the potential location for new sanitary landfill based on weak spot municipalities. Since many factors need to be taken into account to find the most suitable location, we developed STSS to help the decision-making process. So, what is STSS? In short, it is a computer-based system combining spatial data and decision logic to aid the decision-making process. And this is the steps of our STSS methodology. First, we select weak spot input by categorizing the weak spot municipalities into urban, suburban, and rural. The siting of new sanitary landfill is only appropriate for more densely populated areas. Therefore, we only select the urban municipalities for the site selection suitability analysis. We select the criteria based on literature studies and Mexican legislation. In total, we collected over 30 relevant criteria. To reduce the complexity of our STSS and due to the limitation related to availability of data, we choose to select 7 criteria for the final STSS. After that, we classify the criteria into 2 main types, constraints and decision criteria. After the selection step, we assign weights to the 4 decision criteria in order to specify their importance. We choose to implement 2 weighting schemes for the analysis. First, equal weighting, and the second is AHP weighting. AHP is analytic hierarchy process based on pairwise comparison of criteria using a scale of importance ranging from 1 to 9. And this is the weight based on AHP calculation for 4 decision criteria. The next step is to prepare suitability maps for all criteria based on the zones and scale values. As the example, area less than 500 meters and more than 10 kilometers from the settlement were assigned a scale value of 0. The remaining area between these two constraint zones was split into 3 zones with scale value decreasing with distance from the settlement footprint. We do this for all criteria based on the zones and scale values. Then, the suitability maps were rasterized to perform an overlay analysis. So, we can see that in order to get the potential location from each weak spot municipality is pretty long and complex. Therefore, we built a QGIS plugin to automate the process. By using this plugin, the user can independently input the weak spot location and also the criteria layers by themselves. And the plugin will automatically run the whole steps and produce a raster map with scale from 0 to 10. And this is the result from the plugin with overlay score starting from 0 as excluded area into 10 as the best suitable area.
So what is the significance of our results, and what are the main limitations?
First, in general, according to our weak spot map, we think that the waste infrastructure in Mexico should be improved. And also, we provided 3 scenarios for investors to choose based on their preference. Finally, we think that our approach and our selection of criteria can be used for other areas or countries that have the similar development background like Mexico. As for SDSS, we think the most important aspect of our result is to show which area is suitable and unsuitable for landfill sitting based on Mexican legislation. And also, we find an interesting application of our plugin. That is, we can test if the current landfill is comply with the legislations. However, due to the limited time and the working context, our product and our research have some limitations. For example, in weak spots detections, the data sets for generate the factors is not always in the same scale. Some are in the state levels and some are in the municipality levels. And also for SDSS, we think we can include more criteria in our research because it can make a better decision makings. And overall, for our approach, we think we can include more expert opinions to help us to do the better decision makings.
To conclude, the waste management problem in Mexico is complex, making it difficult to know where to invest in new waste facilities. Our group has developed a strategic approach, which starts by detecting weak spots at the country scale and then zooms in to pinpoint where new waste facilities could be built. We hope our results will be able to contribute towards reducing waste mismanagement in Mexico and ultimately reduce the risks to the environment and public health. Thank you for listening. Feel free to ask us any questions.
Super. Again, an impressive video by this group of students. Of course, we also have questions. The first question is by the supervisor of the project, Edward Verbrey. First question, it's your synthesis thesis, geomatics synthesis project. Can you explain the role of geomatics in spatial decision support systems? And would you recommend to have a course in this in a geomatics curriculum?
Yeah, maybe I try to answer that question. For our team, it's quite special case because we're dealing with multidisciplinary. So we're not only dealing with a spatial dataset, but also non-spatial dataset. Like if you see from the video, we did a lot of statistical analysis as well. That's why I think SDSS is quite important, especially when we're dealing with the government to find a potential location. We're not only consider about the spatial, but also the regulation. So if we can have that course, maybe it will be nice.
It's a real addition to the curriculum, you're saying, basically.
Yeah.
Okay, let's see what the other. The other question is by Peter van Oostrum. In more and more countries, waste is considered to be renewable, both in the resources and the materials. Do you have any clue if this already is the case in Mexico?
Well,
and whether it
they
is going
did,
to be economically feasible?
Well, they did try to, for example, construct a waste incineration plant so that the waste will result in energy. However, in Mexico, you also have an informal sector consisting of waste pickers that also used different elements of the waste for to recycle it, to sell it. And those waste pickers actually protested against the incineration plant, which resulted in it not being, being constructed. So although they do have those plans, they do not realize because of the informal sector.
Very good. And then another question by Peter van Oostrum is about the size of the country. Mexico is big, but what was the resolution of your rasters? And did you use multi-resolution detailed grids?
Yeah, Quinn?
Yeah, okay, I can answer this question. For the country scale, we do not use a raster, but we use the shapefile of the municipality level, and we attach the spatial and non-spatial data to that shapefile. So the resolution is not a problem.
Yeah, and also basically that's why we determine the weak spot first, because right now we're working with municipality level for the plugin, and the running process is still quite long. So because we need to rasterize the dataset first and then to do multi-buffer, many stuffs. That's why I think also the size of the weak spot is important to make the plugin run faster.
Very good. Oh, Vera is both doing the multitasking, answering questions and answering them in the chat box. Another question by Edward is basically on the lessons learned on identifying what the real project scope should be. And well, you can read it there. How long did it take you to understand what the project was really about, and what was your role in this? Can someone elaborate on that?
Shall I answer that?
Yeah.
I think in the beginning we had trouble understanding what the client wants, and also to make it related to geomatics.
Vera, you're muted, I think.
Am I?
No.
Oh, okay. So yeah, we had some trouble with that, and it took us a couple of weeks to get a methodology that actually worked. And what was the second part of the question? Yeah, I think.
What was your role in this project?
I think so. In our in our geomatics knowledge that we have now, we didn't have any knowledge about STSS, for example, or also like statistical analysis that we did. So I think that was difficult in the beginning, but we learned a lot from it.
And was anything from the curriculum useful for you to could you apply any knowledge from the curriculum to this project?
Yeah, I think a lot of courses. We did bits of Python coding. We did a lot of cartography, also some legislation. So yeah, I think it was useful.
Quite a nice mix of courses that were integrated here. Then we have a question by Dong Liangpeng. How many waste facilities do you anticipate to build at each site?
I can answer this one. This isn't really something that we had the chance to look into, to be honest. Ideally, if we would have had a bit more time, it would have been interesting to consider how much waste was being produced by a municipality and its surroundings, and then base our spatial decision support system on that. But time constraints didn't really allow that kind of analysis. Yeah, does that answer your question?
So yeah, well, the question that's then the next question would then be how much would that cost, and is it feasible to advise something like that to the Mexican government? And a question I have, and probably it's going to be the last question. You're using the data from the government of Mexico, I think, primarily, and that's of course including the, let's say, the official information about waste dumping and the amount of waste that's been stored in the sanitary landfills. There is also another factor, let's say, burning the waste. Do you think that by improving the access to waste facilities would decrease the amount of waste being burned?
Yeah, if I can answer the question. Rohit?
Can I answer this? Yeah.
Yeah, sure.
Well,
Go
the
ahead.
thing is, our project focused mainly on sanitary landfills for urban areas. Literature research has shown that most of the burning happens in rural areas. So I do not think that it will decrease the amount of open burning, but we did include in our report other methods for rural areas to decrease the amount of open dumping, open burning, and burying of waste. So they are able to apply these methods to do so.
Super. Thank you very much for answering this question. And having said that, is your method also applicable for other situations in other countries? Or similar situation in other countries? Or is this the legislation, for example, in Mexico so specific that it can only be applied to the situation in Mexico?
We do that. Our approach and our selection of criteria can be applied to some areas that have similar background as Mexico, because we have like 3 different categories of our criteria. But we think for social and economy, it can be applicable for other areas. But for the legislation part, we think we have to depend on the situations of that area. Yeah.
Great. Well, thank you very much for your very nice answers. And again, there is the applause just for me, but I guess the rest will join you digitally. Then we take a break for another, let's say, 8 minutes. We will be back at 5 with the announcement of the Geomatics Thesis Award 2019. So thank you very much, Group 52 Impact, and we will be back at 5 on this YouTube channel. Stay tuned. Bye. Welcome back. Geomaticsday 2020, we are almost at the end. We're now going to announce the winner of the first Geomatics Thesis Award 2019. We have 4, we could say, already very good nominees. The first nominee is Vasilius Bouzas, who has written his thesis on the structure-aware building mesh simplification. Then we have Xianglang Du. Her thesis was on accurate, detailed, and automatic 3D modeling from point clouds. Then Malika Sayadian, she wrote her thesis on spatial and temporal analysis of deformation based on remote sensing and subsurface exploration. And then finally, the final nominee is Dimitris Xenakis, whose thesis was entitled Placement Optimization of Positioning Nodes, Maximizing the Distinction of Indoor Zones. Well, those were the theses. We had a very knowledgeable jury that assessed the thesis and came to a conclusion. The thesis committee or the jury consists of Kotrinja Valekaite, as now working for Arup, but also was a Geomatics graduate. We have Thijs Brentjens, who has his own company, also a Geomatics graduate, but then from a long time ago, from the, what's it called, Geodetic Engineering program. And finally, the chair of the jury is Professor Lars Bodem from Aalborg University in Denmark. And I think I can give the floor now to the chair, to Lars, who will announce the winner of the thesis award. Lars, the floor is yours.
Thank you, Bastian. Thank you for having us here. And on behalf of the jury, thank you for inviting us to evaluate the candidates and motivate the decision on who will receive this prize for the best thesis within geoinformatics in 2019 from this program. I'm impressed by the whole setup here. I've enjoyed some of it, and the inspiring program of the whole day. That's really well done, guys. Really amazing what you've managed to put together on this day, and we are very pleased to be a part of it. It's been a serious field of contenders, I will say. We've had the pleasure of reading some really good reports presenting high-profile research. All of them showed impressive results and very innovative solutions to the research questions that were formulated. So it's really a tough job to name a winner here. So what did we look for? Yeah, we had 3 criteria that we evaluated from. The first one was innovative research methods and how to solve the problem. The second one was reproducibility and replicability of the scientific work. We find it very important that you are actually able to do the setup and the work again. And then the third one, solving societal challenges in a broader perspective. We also think that it's very important that your work in some way is solving some of the larger societal challenges that we have around. But that process didn't get us the whole way because they were so good. So we took yet another turn in the assessment, and that was very much related to communication of the work done. The readability of the thesis and the presentation through the use of graphs and illustrations and so on, which is also a very important part of communicating research. This is in fact something that requires very good skills and high qualifications to be able to communicate complicated matters in a transparent and consistent way. So if a thesis is written good, it also makes it easier for others to build on top of the work done, and it adds to the value also for society and reproducibility too. So you can say, if you are good at writing and you are good at presenting, then you also will fulfill some of the original goals that we set up. And here we found one thesis actually that has impressed us all. And this specific one is both very qualified and highly reproducible through the comprehensive guidance in use of software and the availability of the original data also, which is also very important. It will undoubtedly become an important part of solutions when we talk about global environmental and climate challenges. And furthermore, this thesis was extremely well structured, and the fluent writing made it a pleasure to read. Beautiful illustrations and the related explanations tells a story of its own. This thesis is a really worthy winner of the best thesis within geoinformatics in 2019 for TU Delft graduates. So I have to announce the winner now. The winner of the prize, Best Geoinformatic Thesis, is Xinglan Du. Congratulations.
Oh.
Congratulations.
Congratulations, Xinglan.
You did a very nice job.
Can you hear me?
Yeah.
Yes.
Oh, good. Thanks for giving me this award, and I really appreciate that. And like during the thesis, I felt like at first I was kind of frustrated because I didn't know C++. I didn't know like the theories behind, but I received a lot of help, not only from Liang, who is my mentor, but also from Vasilius and Likos and many other classmates. And yeah, I really appreciate that. I will continue to work hard. Thanks.
It's so well earned. Congratulations.
I'm so excited.
And of course, Lars handed over the certificate, which you will receive sometime, hopefully next week, in the mailbox. But it also includes a prize of 500 euros to be spent on anything you would like to spend on. So that's also coming in your direction. Of course, we have to share your contact details with each other, but we don't do that here on YouTube. So congratulations, Xinglan. We will be in touch. We're almost also now at the end of the Geomaticsday 2020, but we don't do that before thanking some people. Of course, the jury members. Thank you very much, Katrina, Lars, and Thijs, for your thorough work. Was really impressive how you came to a conclusion, very structured, and we really had nice discussions there. But I don't have, well, I thank you, of course, but you're not the only ones. We also have our secretary, Martine de Jong Landsbergen. And normally you would give flowers to them, but there are no digital flowers available, unfortunately. But Martine, thank you very much for all the support on the back end of our organization. And of course, we have to thank our sponsors, which are CGI, Sensing, Sweco, and Fugro. Thank you very much for supporting us also financially. And of course, finally, we have to thank the student assistants, Laurens van Rijssel, and for today, for sure, Mel Smith, for organizing it so well that we didn't run into any issues. So Mels and Laurens, thank you very much.
No problem.
A final, but you're not done yet, because we are now going into the online drinks, and I guess you have to share this link where people can access the Discord meeting rooms on YouTube. Then
well, the link actually is already in one of the brochures. Is it already somewhere?
I'll share it again, and we'll meet each other in the meeting rooms in a minute. Thank you very much. Hope to see all of you sometime, someplace in the Geomatics program. Might be next year in the Geomaticsday 2021, live in the Faculty of Architecture, or maybe online. We don't know. We'll see. But thank you very much, and I'll enjoy the rest of the weekend. And we'll see you in the meeting room. Thank you very much.
Sure. Thanks, everybody. Bye-bye.
Bye-bye.